Deci noi am transmis că limba oficială a conferinței este engleza, dar putem merge pe această paradigmă dacă sunt studenți care preferă, să zicem, sunt de la secția română și preferă să prezinte în română, decât ca să cădem de acord aici cu toți. Oare bine așa? Hai să mă consult cu reprezentantul nostru în panel.
Da,
e în ordine, da? Okay.
Deci, să spunem așa, în principiu este în engleză, dar dacă cineva preferă în limba română, o poate face fără nicio problemă. E bine așa? Ca și regulă, probabil ca și anul trecut, fiecare ne prezentăm studenții de la universitatea noastră, da?
Da, deci te referi la faptul că ceea ce trebuie anunțat ca lucrare care urmează a fi prezentată, fiecare își anunță studenții aparținători universității pe care o reprezintă. Da, deci clar. Eu voi intra și la celelalte paneluri să mă asigur că și-au dat drumul așa cum trebuie și voi reveni. Mulțumesc!
Deci mai sunt 2-3 minute până începe prima prezentare. Până atunci să spunem studenților, bine ați venit la această conferință studențească. Vă felicităm pentru faptul că ați optat pentru a vă prezenta lucrările în cadrul acestei manifestări. Cu siguranță toată lumea va avea de câștigat. E în primul rând o conferință și abia după aceea și o competiție. Deci vă rog să tratați acest eveniment ca și o conferință. Da? În primul rând, aș zice eu. Și din această perspectivă, toți participanții vor avea de câștigat. Vor vedea cum se prezintă ceilalți colegi, ce subiecte au tratat, care sunt subiectele de interes în anul 2021. Eu zic că e un eveniment interesant și cu foarte multe lucruri de învățat. De asemenea, pentru foarte mulți studenți este o preprezentare a lucrării de licență, respectiv a lucrării de master. Și din această perspectivă, eu zic că aveți de învățat. Vă rog să țineți cont de eventualele recomandări, observații pe care le vom face pe parcurs. Ele nu sunt doar cu scopul de a vă critica, ci mai ales cu scopul de a vă îmbunătăți prezentările viitoare.
Okay, thank you. First of all, I will ensure that you saw my screen. Can you confirm, please? Okay. Hello, everyone. My name is Christian, and my paper topic is about applications of artificial intelligence in evolutionary art. Even with nowadays technologies, there are some fields in which humans are irreplaceable. Some of these fields are justice or art, and the last one will be the field we are going to talk about today. In my paper, I try to use several approaches from artificial intelligence in order to generate artworks. And for this goal, I set a couple of objectives, as studying the existing approaches in the literature, comparison and the implementation of this approach in order to determine if they are effective or not, and proposing of improvements to existing methods and creating of new methods. And the last one is evaluation of results obtained from the experiments. So first of all, we're going to talk about genetic algorithms. This is a meta-heuristic algorithm from the class of evolutionary algorithms inspired by the natural selection process. Since we are searching for generating an image, our solution will be an image as well, represented by a matrix. And our methods require input image, as we can see here. This is an input image, and try to optimize the fitness function. As a natural choice, we choose our fitness function to be the difference between this generated image and the initial image, and we take the Frobenius norm from this and try to minimize this distance. So our algorithm initialize a population of individuals, and each individual is initialized by a matrix of zeros. As we can see here is a black image, and after that in initialization algorithm applies a couple of shapes, in this case are lines at different sizes and at different random positions. And as the evolutionary process goes by, the algorithm selects parents from the population, do a crossover operator from them, and gets children from these parents. The crossover operator is defined as adding a weighted sum of these two matrices of the parents. And the selection is a fitness proportional one, which means a parent with better fitness will be more likely to be selected from the population. And some of these children are mutated. And this mutation process means that on our image there are added some of these shapes. And as the evolutionary process goes by, we end up with an image like this one, where we can see that it tries to imitate the input image. A natural question here will be if our algorithm will receive the global optimum, and the answer is no, because we are using a finite number of geometrical shapes. And if we are trying to get to the global optimum, which means the input image, an image generated one-to-one to the input image, that will means that runtimes will go to infinity. But this is not our scope. Our scope is to get the input image and try to stylish it. And here are some more examples of art generated in this way. Here are naturemort, landscapes, and some existing artworks, and we can see what or how our process generates image. As some of you may have observed, our approach needs a set of parameters, and to choose the best parameters, we run out a series of experiments with a different set of parameters and compare the values of distances. In this slide, we can also see graphics where each pair represents comparison for different parameters, like mutation rate or elitism rate and so on. Next on our today's list is an approach that uses pixel characteristics for different parameters. And here we use a particle swarm optimization algorithm. And as we can see in this flowchart, we define our fitness function as a weighted sum of two functions. Here we can have or not on imitating target image. We can see here this is an optional part. And if we don't have it, we use just these aesthetic fitness functions. These aesthetic fitness functions are generated by genetic programming algorithm, or we can choose them from a pre-settled list of such functions. And here we can see that our algorithm is initializing the particle's position regarding to a random initial artwork, or can initialize the particle positions with random positions. A particle, in our understanding in this approach, is a pixel with which has a fixed position in the image and variable position in color space like RGB or HSV, and moves in color space to get the global or local optimum. And finally, we are getting an output artwork. This approach is not new, but in the associated works, they describe a fitness function like this one here. And we can see here, because of two sums, the temporal complexity is O of n squared. And we try to reduce it to O of n O of 1 with replacing this fitness function with this one. But the issue here is that we are looking only on a certain pixel and try to optimize its value, and not taking into consideration the neighborhood of a pixel. Because of this, we don't use a global topology as in the associated artworks, in the associated papers, but uses a von Neumann topology that looks to a local characteristic of the pixel. And also we studied multi-objective optimization algorithms. And on the next slides, right here, we can see also that, as in previous method, we do some parameters tuning. And here are the results. This results at the top is without a target image. Here is results from a classical PSO and multi-objective PSO. And here the results with a target image. Also classical and multi-objective. We can subjectively say that multi-objective PSO handle better with the task of generating images. All right, and next on our list are result analysis. To evaluate our results, we set up a questionnaire that contained two questions of for each of 18 works of art which were prepared. Six artworks were from PSO algorithm, 6 from genetic algorithm, and 6 real artworks made by humans. And the two questions that were presented to the responders were if this artwork is created by human, with answers like yes, no, or not sure, and to evaluate the artistic sense of the artwork and give it a mark from 1 to 5. In our statistical test, in our questionnaire, a number of 51 people get involved. And here we can see the distribution over genres and age. And here are the results of the questionnaire. We can see that in terms of comparing pixel-based approach and the genetic algorithm approach from the point of view of it is human-made or not, a number of 24% responded that artworks from genetic algorithms were generated by human, and 70% that at the PSO. we can see that we are far away from human-made real artworks, but in terms of comparing these two artworks, we can say that these two approaches, we can say that genetic algorithms deal better in this case. However, in the terms of aesthetic scores or artistic sense of the artwork, humans evaluated better the PSO algorithm rather than a genetic algorithm. In conclusion, we can say that in this paper we've illustrated different ways of generating artworks, improved some existing approaches, and give a new approach as with genetic algorithms. And our experiments and our questionnaire performed a comparative analysis of this approach. And here we can see the advantages and the disadvantages of the proposed method. As further directions of research and development will be reduction of time complexity, because these algorithms require a lot of time to run, and hybridization, maybe to unify these two approaches into one. From our perspective of AI, can be generative neural networks, data clustering algorithms, reinforcement learning system, and even we can use mathematics for this using fractal geometry and so on. And now it's time for your questions. Well, as I said, I set a run of... Aș putea să răspund în română la întrebări. Bun. Deci, cum am spus, am setat o serie de experimente în care am încercat diferiți parametri. Practic, algoritmul, să zicem că avea un set de n parametri și la care schimbam doar unul dintre aceștia și comparam cum se comportă funcția de fitness, ce valori atinge când se schimbă un anumit parametru, iar pe restul îi lăsam la fel. După aia schimbam tot așa câte unul. Deci, ei în lucrările de specialitate au folosit funcția aia de fitness pe care am arătat-o, iar eu am încercat să o optimizez. Ei nu dau, adică din câte am văzut în lucrările lor, nu dau timpii de rulare, însă eu am implementat și lucrarea lor cu funcția aia de O de n pătrat, iar timpii de rulare sunt foarte mari pentru că aia e o singură evaluare de fitness, dar în populație, adică în populația de particule avem atâtea particule cât e rezoluția imaginii, adică înălțimea mulțit cu lățimea, și toată asta, adică înălțimea ori lățimea ori funcția de fitness, care e o de n la a doua, mai merg într-un for care îi pe iterație, adică un număr de iterații, și în total se primește o complexitate de O de n la 5, iar eu am redus-o la una de O de n la 3. Oricine era invitat să participe, fără cunoștințe, adică dacă de domeniul artei au fost mai mulți implicați studenți de la Mate Info și cunoscuți. Iar aici am și o aplicație, dacă mai avem timp o să ruleze imediat. Am făcut o aplicație care ia imaginea asta din stânga și arată aici cum un algoritm genetic sau un particle swarm optimization. Aici am mai multe implementări, dar în articol nu am avut decât 8 pagini, o limită de 8 pagini și n-am putut să trec totul. Ok, am dat run.
Pentru că timpul e scurt, nu o să mai pun întrebări. În schimb, pot să vă spun că acum câțiva ani am dat peste ceva instrument software care putea să transforme o imagine oarecare într-o pictură, într-un anumit stil de a picta. De exemplu, cele mai interesante erau cele care transformau o imagine reală într-o poză impresionistă. Puteți să spuneți eventual ceva?
Am studiat și abordarea asta. Se folosește o rețea neuronală de tip style transfer, adică sunt două imagini, una de target, cum ar veni, și una de stil. Și ar veni că la output iese o imagine pictată în stilul imaginii de stil. Adică imaginea de target iese în stilul imaginii de stil. Se folosesc encodere și rețele neuronale pentru asta. Nu am scris despre asta în articol.
Da, mulțumesc.
Și eu vă mulțumesc. Și aici putem vedea și cum merge procesul.
Da, dacă îmi permiteți, este vorba de un student de la Universitatea Tehnică, Paul Rednick, sper că este printre noi. Ne va prezenta o platformă care cu siguranță va ajuta cei interesați în dans să se cunoască mai bine și probabil să învețe anumite stiluri de a dansa. Mă înșel sau
nu.
Despre așa ceva este vorba?
Exact.
Aveți cuvântul.
Mulțumesc. So, I will present in English. My name is Paul Rednick, and today I will present you DanceSpace, which is a mobile app that has social media and intelligent learning platform capabilities. I will share my screen now. Just a second. Do you see the presentation or no?
Yes.
Okay. So first of all, introduction about dancing for everybody. Dance sport is the sport art that regulates dancing in general. Dancing has many styles, many different styles, and a huge community from social dancing, breaking, and dance sport. All are included here. And also dance sport will be in the Olympic Games in 2024 with the breaking discipline. The idea of this project was that during the pandemic, mainly, dancers could not be connected anymore with each other because we had no competitions and we had nowhere to practice. Studios were closed. So we had to find new ways to stay motivated, and we couldn't find any, honestly. So this app aims at that. I'm doing this project about dancing because I'm also a professional dancer, and I feel like something like this would be really useful for our community. Some objectives. So as I said before, it is a mobile app, one developed for iOS systems at the moment. And the main goals are to connect dancers, teachers, and choreographers worldwide, to provide dancers all the information they need about their professional careers, to find new learning tools for the dancers to improve their dancing, and to create a kind of like marketplace for them. For the related work part, of course, we have a lot of mobile apps on the market, like there are millions of apps. We will take some features from popular social media apps and sports apps. As you can see here is a screenshot from Instagram. So we will take some of the features from this kind of apps because people are used to seeing this in their everyday life. Mobile apps are really good because you can take them everywhere, basically. They work better most of the times than their web counterparts. And also you have all the sensors and the camera directly on the device, which helps a lot, especially in our case, you will see. Then we have the WDSF website. WDSF is the World Dance Sport Federation. Here we can find all the information about the professionals and we will include their information in our app too. We have different learning platforms that became very popular during this pandemic. And yeah, video tutorials or lectures online are everywhere, so we will include this as well. Then we have some demo apps from Apple with their Core ML. Core ML is for machine learning on iOS devices, and they had some fitness apps that are out there. We will take some of the features of those apps and include here. And also we have Just Dance and other similar games on consoles. Just Dance is similar to what we will do here, but it's more for the fun part and not for the professional part. Now, as for the technologies, as I said before, it's an iOS application. We need an iPhone or iPad with a quite new iOS system. Also, LiDAR sensor would be great because we will need it for machine learning part. And all the application was done on Macs because on Xcode with Swift, only on Macs available. Other technologies that I used include kits from Apple, like UI kit for the UI part, Google Firebase for the backend, ML Core, ML Create, also provided by Apple, AR kit for the augmented reality part, and the WDSF API. I gained access to that from WDSF. The architecture of the application will look something like this. So we have the front end, which is on the mobile, then the logic, and then we connect to everything that I described before, Google Firebase, the API, ML Core, ARKit from Apple. So now the application will have 4 sections: the newsfeed, information for professionals, learning platform, and marketplace. And I will describe all of them now shortly. The newsfeed is what you can expect from a social media app. You see some screenshots here. So you have a profile, you can post photos, videos, articles, anything basically. You can interact with other users by commenting, by liking their posts. And yeah, that's basically what you find here, what you have also in other social media apps. Then for information for professionals, we took information from the API of WDSF, and we just get results, competitions, calendar, couples, all this kind of official information, because I wanted all the dancers to have this information directly into the app and not have to go to their website anymore. Now, the most interesting part is the learning platform. Here we have a dance moves recognition system with machine learning, which you can see a picture here on the side, which will recognize dance moves performed by dancers, then an augmented reality tutorial, and also we will have some music, some books, some history about dances, so basically some information also. Then the marketplace, here we will use the map mostly for the find a studio, and then dancers can buy and sell costumes or find a partner nearby, things like this. Now for the dance moves recognition systems, I used Create ML. How it will work, it will take 19 points from the human body, and it will understand how they move across the video. It will split it in different frames, and then it will use a classification algorithm to create a model, to train a model, and then it can recognize the figures. So it's a classification algorithm. The augmented reality part, as you can see here, maybe this seems like a gimmick, but it's useful for dancers to be able to see the teacher or the dancer that performs from any angle. So from the back, from the front, from any angle you want. Here the model is created with a LiDAR sensor, with a 3D sensor, and then it's animated with the movements, and then it will be loaded into the app, so everybody can see it. For the API, here you can see from the API a snapshot. we will download it as JSON, all the information, and we will use them inside the app. And the API has 7 entry points like couples, competitions, calendar, things like this. The Firebase is used for the backend part. We have authentication with Firebase. We have storage for different media types and also a database functionality. So everything we basically need for the backend, and it's easy to implement with iOS. That's why I chose Firebase. Now, for the data of the app, as it's a social media app, most of the data comes from the users directly, so they post photos, videos, and other stuff. Also, we have the information from the API of WDSF, as I said before. Some tutorials of some choreographies, dance music will be added in the beginning, so by the admin, and all the users will see them. And also we have the data set for the dance moves recognition systems, which I created from scratch. Now, how I created this, basically I took dancers from all around the world, really top dancers, I mean world champions, national champions from more than 20 countries. And I created 5 choreographies: waltz, tango, samba, jive, and disco. I made them dance those choreographies, then split each figure alone into a separate video, and each figure basically is performed around 50 times because I asked 50 different dancers, more or less. Then also we have some other movements like walking or stretching in a folder like other movements, to be able to recognize those as well, not only dance figures. And for the videos, we needed the camera to be fixed, the whole body to be visible all the time, the background to be quite clear, and videos are processed at 30 frames per second. It could be done at 60 also, but I use 30. It's good enough, I think. Now, why do we need many different dancers? Because as you will see in these videos, 3 different top dancers will dance the same figure in a slightly different way. So for our system to work the best, we need to find those small differences between how the dancers perform a different move. And now some results of this system. As you can see here, we have some figures and the precision with which they were learned by the system. Some of them worked better, some of them not so good, but overall the results were quite okay, especially in complicated moves where turnings were involved or where longer moves were performed. Then it didn't work so well. You can see an example here. An oversway performed by me, and you can see how the points are taken from the human body and the precision with which it understood that I do an oversway. This is a figure. Okay, and other general results include a user-friendly interface, which is easy to use and understand, good flow of the app, features working properly, so no bugs. And also the app will work on different iPhone devices. Okay, older ones will not support some features, but still it will work. And also the dance moves recognition system works quite well. As an overall, more than 80% of the moves are understood by the system when they are executed in front of the camera. And that's basically it on bibliography, and that's it.
Thank you very much for the presentation. It was very interesting. Now, I'm a little bit confused because you presented a lot of functionalities. Some of them are implemented in the tools you are using in some libraries. Some were implemented by yourself. And for me, it's a little bit hard to separate the two parts. What you effectively implemented and what was borrowed from libraries. I may say that it's okay to use tools to borrow different libraries, but in such a presentation, you should emphasize the line between the two parts, the taken part and what you were developing. So, can you do that?
Yes, so actually the tools only helped in certain areas, so it was no code or no functionality implemented. I implemented everything basically. Okay, in the Create ML, as I said, it's an algorithm that is provided by Apple and it's not visible to the users. It's a tool, basically a software tool, where you add your videos and it will automatically train your app. So I didn't do the processing parts. That's what I didn't do. Then for the social media part and for the marketplace and things like this, every functionality was basically implemented by me. Of course, I need some libraries to take the map, for example, from the phone or to use the camera. But other than that, I implemented them by myself. So it was not taken. I didn't have any functionalities taken from other sources.
For instance, that part with, as I understood, 19 points of body was taken, or it's your own development?
That's what I said, that Create ML is a software provided by Apple, especially for their iOS machine learning application, so for the developers. The algorithm behind is not visible for the people. You just add the videos, it shows you how they process the images, but you don't actually know what's behind. And it will return.
Okay, thank you. Unfortunately, because the time is limited, if my colleague wants to put one question, if not, we can go on.
Yes, sure. I will share my screen. Please tell me if you can see it. Great. So my name is Vasilika Andreea Moldovan, and I'm a student at Babeș University. And today I will talk a little about skin lesion classification using deep learning. And I will start by saying a few words about skin cancer diagnosis. Most of the medical methods used by dermatologists imply a visual analysis of the lesion in cause, and that is why deep learning and machine learning in general might be a good choice when talking about skin lesion classification. I have an example here with one of the most known such methods, which is ABCD method. And this refers to the asymmetry of the lesion, the borders irregularity, the different colors which appear in only one lesion, the diameter, and evolving of the lesion growing over time. Other known methods are 3-point checklist rule, 7-point checklist rule, and so on. Those methods were also done for non-experts to see that something is not as it should be regarding a skin lesion and to go to consult a dermatologist. But it must be mentioned that skin cancer diagnosis cannot be put without skin biopsy done from the respective tissue. As the motivation behind this paper, was the increasing number of skin cancer cases discovered every year. World Health Organization estimates that by the year 2025, the number of skin cancer cases will grow by 20%, and by the year 2040, the number of skin cancer cases will grow by 74%, which is alarming. Also, another good thing, actually this is the good thing, the other one was not good. A good thing regarding this is that there is a high probability of survival if discovered early. Statistics show that the 5-year survival rate of skin cancer can be 99% if discovered early. And another thing which is encouraging is that some symptoms might be quite visible, even for non-experts, such as different colors in the same lesions or asymmetry of the lesions or so on. And another motivation was represented by the importance of raising an awareness regarding this disease, because it is very alarming because of the UV radiations and the sun exposure, and it is important to raise an awareness regarding this because we can stop it and we can slow it down, and it really is something which is in our power. And the symptoms are more visible and more easy to be seen by normal people, by non-experts, than they are for other diseases. Okay, and now the problem definition and the challenges which came with it. So the problem itself was represented by classifying dermoscopic images in order to determine their nature. And the first aim was to classify those images into 2 classes, malignant and benign. And then after I've used the dataset provided in ESIC 2019 competition, that dataset was split into 9 classes. 8 of them are listed here, are melanoma, melanocytic nevus, basal cell carcinoma, actinic keratosis, seborrheic keratosis, dermatofibroma, vascular lesion, and squamous cell carcinoma, and there was another unknown class. I chose to also try to classify the dermoscopic images into those 8 categories because some of them are malignant and they represent risk, but also those which are not malignant are either quite common, as melanocytic nevus is, which is the mole, the usual mole, and the other ones, which are benign, are quite dangerous and can lead to complications. Some challenges which came with this problem were represented by the fact that the dataset wasn't homogeneous because the dataset was quite big, had to be found for mobile integration in order to make this classification more open to every person to use it, not for dermatologists only. Okay, so as I said, regarding the literature review, many researches have been done on this topic, classifying either the images into 2 categories, malignant and benignant, or in 8, 9, or more even. But the most downside of them was the fact that the most performant models required a large amount of memory and an increased period of time for making the predictions, making them unsuitable for mobile application and for day-to-day use. Okay, I'm sorry if I'm going too fast, but I'm trying to get into time. Do you hear me? Is it okay?
Yes, it's okay.
Okay. Yes, I'm not seeing. I'm seeing only my screen, and I'm afraid to not talk alone. So regarding the image preprocessing and data augmentation, as I said, the dataset used was quite imbalanced, and it required image preprocessing and data augmentation. Some models were also trained with additional data. For resizing the images, different cropping strategies were used, but the best one and the final choice was represented by center cropping. Here we also went with the premise that the user will center the legend in the image, will focus when taking the picture. Also, color consistency techniques were used. Many from the literature review were tried, but the one which behaved the best was represented by the shades of gray. And data augmentation techniques were used. Here I used the augmentation library from PyTorch, and it provided random flipping, random rotation, random scaling, transpose, cutout, and even auto-augment policy. Okay, regarding the architectures, several architectures were considered here, among which EfficientNet, ResNet, CNet, DenseNet, Inception v3, VGG, and MobileNet. Those were the architectures which gave the best results when it came to image classification in the literature review. And also MobileNet was considered because one of the aims of this study was to find an architecture which behaves well on a mobile application too, which can be integrated in a mobile application without taking a long time in order to complete the predictions or to require a large amount of memory. So MobileNet, being designed specifically for mobile application, had to be taken into consideration. Those architectures were tested and experimented using different consideration, and parameters which were changed were the learning rate, the number of training epochs, the activation function, and the pooling strategy. The best results will be presented a little bit later with the associated parameters. And also for increasing the accuracy and the performance of the model of the system, ensemble learning was considered. This type of learning combines different models in order to produce the best predictive model, obtaining the prediction through majority of voting. The models which compose the ensemble can be chosen in different ways, can be chosen randomly or so on, but in our approach, I chose the best N models where N took the values 3, 5, 10, 12, and 15. And now a little comparison regarding the results. For evaluating the results, I used the area under the curve because it illustrates the performance of the classification algorithm at different points. The accuracy of the models, and also the recalls, because it shows how accurately the model identifies relevant data. And the models which behaved the best were EfficientNet and DenseNet in generally, but here I presented the best model, the best obtained results for every family of tried architectures. And it can be seen that there's a little bigger difference between the result obtained by EfficientNet B3 and the result obtained by MobileNet. With the downside that EfficientNet B3 requires a larger amount of memory and a larger prediction time than the MobileNet, but it receives a higher accuracy. In the table from the left, it is presented the experiments regarding the ensemble. As I said, I had ensembles being composed from 3, 5, 10, 12, and 15 models. It can be seen that the larger the ensemble is, the higher the performant is the system. But we have here the downside because we don't have the time and the memory required by a mobile application. So putting everything in balance, the final solution contained an ensemble containing only 5 models, the one composed from EfficientNet V3, EfficientNet V4, CRSNet 50, DenseNet 101, and CRSNet 101, even though the larger ensembles behaved better and obtained better accuracies and recall and so on. And here I also have an analysis of how well the final ensemble behaved on each class. So it behaved better on vascular lesion and dermatofibroma because those lesions are more visible and more distinct than the others. And it behaved good, but not as good as for vascular lesion, for melanoma, melanocytic nevus, and squamous cell carcinoma, because those lesions are quite common and they can be confusing sometimes, even for experimented dermatologists. Okay, so I will show you a little first the application. Just a moment. I will show you one example of vascular lesion because can you see the screen of the phone? Great, thank you. Because as I said, it is quite different. It's more red than the others, and we can see that it obtains a great probability of being a vascular lesion and so on. Another one will be dermatofibroma. This is again a little different in the shape than the others, and it is obviously why the models behave better and achieve a greater accuracy on these classes than the others. And if we take a simple mole, this will be probably a melanocytic nevus, but the probability is not as high because the model is not as performant as it was for the classes which are more distinct and have individuals characteristics. Regarding the future works, there is place for many improvements in the future works, mainly because one big downside of this was the fact that the training phase took a really long time. Training one model on the entire data set of 25,000 images took around 23 hours. And it made the process harder. One important improvement is represented by the fact that a better performance can be obtained using a larger ensemble, but here we had downside with the time and memory constraints, and some work in this area will improve definitely the application. And I think that is it from my side. Thank you. If you have questions. I also tried average, but the majority of voting behaved better. I tried only this two. I split the data set, but I also tried to train on all the data set, because the ISIC has also a 2020 edition, which has a larger data set of 30,000 something images, and I kind of combined those.
Just a short question, because the time is again against us. Do we really need multiple models to recognize skin cancer, or if we do better tuning of one model, we would get a good result? What's your personal opinion after this research?
We don't necessarily need multiple models. I wanted to try this approach with ensemble learning because it increases the accuracy, and it gives a higher accuracy than my individual models did.
Okay. Thank you very much. I think we can go on to the next presenter. It's from the Technical University. Alexandru Motiok will tell us about machine learning in detecting customer purchase behavior.
Hello?
Yes, we are listening.
I'm going to share my screen. Tell me if it's all right. Can you see my screen?
Yes.
Okay, let's start. So, hello, my name is Alexandru Motiok. I'm a student at the Technical University of Cluj-Napoca. Today, I'm going to present to you the research paper entitled Machine Learning in Detecting Customer Purchase Behavior. As a summary, we are targeting the induction of the adequate data mining techniques in the context of forecasting customer behavior. Additionally, we will address the advantages of pre-processing and clustering our data in favor of obtaining optimal results in terms of prediction accuracy, as well as other evaluation metrics that we will discuss later in the presentation. More simply, we want to run a comparison between a series of machine learning techniques to reflect on which model would fit the best in the field of e-commerce and marketing. Moving to the table of content, we will cover the following 6 sections. The first 3 sections we will discuss the theoretical aspect of our research, while the rest of the section we will focus on implementation and experimental results, and finally a conclusion with some future resolutions. So let's start with the issue at hand, the introduction of our article. Let's talk about data. With the tremendous amount of data at our convenience and such high processing power, data has become a new form of asset. And simply explained, there's a high demand of data due to its strategical value. Before moving on, I want to discuss the problematic of our task. First, we face the challenge of using all the available data in order to produce meaningful and actionable information. More specifically, data that holds economic value. It is in the quantification of relationships and patterns around customers, products, and markets that drive operational and strategic predictions. Also, in the current research in the field of artificial intelligence for user modeling, it has witnessed tremendous effort, but on the other hand, on the field of marketing for the retail industry, it doesn't have too many applications. Our motivation is designing a proper implementation that can be furtherly expanded for the use of marketing professionals in the e-commerce field, and for sheer curiosity for the state of art regarding machine learning in the area of marketing. So what we can expect from the future, from data mining? The process of data mining will only grow in popularity in the future, considering the fact that data is going to continue to grow in the future due to the implication of social media and social networks such as Twitter and LinkedIn, those companies already make use of their large amounts of data and processes for their own marketing purposes. With that being said, any organization that has data and processes can be analyzed through data mining, resulting in the extraction of actionable information. In the information economy, the most appropriate method to extract strategic value is through data mining. So we will work with big data. So what is big data? What challenges do we face when working with big data? Big data is an important challenge for marketing professionals, given the fact that they understand the effluence of knowledge that they can deliver from machine learning systems, but only if the right tools are used. And manual reporting methods are not efficient in discovering important customer insights hidden in big data. That's why we aim to automate this process. And with that being said, there are a few steps that need to be followed before creating knowledge from patterns. The first step is data cleaning, the process of preparing raw data and for analysis by removing bad data. In this step, the noise and inconsistent data is removed. Next, we have data integration. That is a data pre-processing technique that involves combining data from multiple heterogeneous data sources into a coherent data store and provide a unified view of data. This step is necessary when working with multiple databases. Data selection, this is where data relevant to the analysis is extracted. And data transform. In this step, data is transformed or consolidated into forms of appropriate for mining by performing summary of aggregation operations and normalization. For our approach, our focus is on supervised machine learning methods, where we construct a model from label training data. This model will describe the relationship between the features and the labels and allow us to predict if a customer will get an individual label based on a set of features related to that customer. Organizations using predictive analytics for their sales and marketing efforts made more than half the sales than those that did not employ such techniques. So using this type of forward-looking perspective of the future, organizations can create and implement more successful sales and marketing strategies, increasing customer satisfaction. So we will correlate data sets from retail companies that contain demographic information and information about clients to find an economic model that predicts what will be the customer purchase behavior. And according to a study called segmentation-based modeling for advanced target marketing, those mining techniques can help retailers find these goals in order to implement customizable marketing campaigns, which will be much cheaper than mass marketing campaigns. Raw cell data could be consolidated into databases containing details about each transaction, prices, number of items purchased, and so on and so forth. Users can then leverage the database to get a full customer purchase behavior. And finally, the companies will have an economic benefit from this approach. So next, we'll discuss about the incorporation of quantitative methods that through some statistical type of inference testing will extract trends and patterns. That is called data mining. What mining techniques we will use? For our approach, we'll first use the KNN lazy classifier, which is an easy to implement supervised machine learning algorithm that we'll mainly use as a baseline for our models comparison. Next up, we have naive Bayes, which employs the probabilistical epinomous theorem and additionally for our approach, we are looking specifically at Gaussian naive Bayes that follows normal distribution and supports continuous data. J48 decision tree. This classifier is a simple implementation of the C4.5 algorithm, which is an extension of the ID3 decision tree used for classification purposes. And finally, we'll use random forest tree. Well, random forests are a way of averaging multiple deep decision trees trained on different parts of the same training set with the goal of reducing variance. This comes with a small increase in bias, but generally greatly boosts the performance of our final model. And for our data set, we will start experimenting with a database from a retail company who wants to understand the customer purchase behavior, specifically the purchase amount, and this will be made against various product categories. The content of the available part from the retail database, it is a summary of data from various customers for selected high volume products with data from one single month. This available data, as we can see, we have about more than 500,000 records, each record being a specific order that contains demographic data about customers, such as age, gender, occupation, as well as product category description. And as a theoretical prerequisite, we will consider every data sample as a transaction defined by a set of items. In the next slides, I'm going to quickly go through a few charts that describe the demographic representation of our data set, which will give us an initial insight of what we're working with. This is a chart representing the gender and age demographic of our customers. This is a city category representation, as well as a longevity in terms of how many years has a customer stayed in his current city. And a chart representing the most revenue generating product categories in terms of average purchase amount. And our target class for our classification problem are the following attributes: the discrete yes or no value, describing the heavy spenders, as a continuous value, describing the overall purchase behavior. Even after the discretization in the attribute describing the overall customer purchase behavior, which encompasses both total and separate purchase value, it has around 50 possible values, and such it is a very difficult target class for any machine learning approach. And while research in marketing and AI focuses on the analysis and design of learning techniques, the interaction of data mining with the preceding phase of data preprocessing has not been investigated in detail. So the impact of different preprocessing techniques and partitioning, it is assessed on a real-world data set used in marketing of a company from a retail industry. Our case-based analysis provides empirical evidence that data partitioning and clustering in the pre-processing phase of our approach has a significant impact on the predictive accuracy. Well, for our workflow, we're going to use distributed machine learning, which consists of multiple sites of data and computation. We want to compare the results of distributed approach of machine learning in the case of customer purchase behavior data mining. This is because the emergence of big data demands a growing need for analyzing data using distributed systems, because it is too much for a single station to handle. One of the two assumptions is commonly adopted to how data are distributed across sites: is homogeneously or horizontally partitioned, or heterogeneously or vertically partitioned. We choose to implement vertical partitioning to our data set, comparing different sets of features in relation to the model performance. Data partitioning is also useful in order to avoid the thrashing of memory management systems, which occurs when algorithms attempt to process big data sets in the main memory. if a learning algorithm complexity is worse than linear, then processing smaller sized data subsets sequentially can make it linear, allowing a system of distributed processors to data mine the subsets concurrently. Here is an example of how our data clusters will look. For our first cluster, we will focus on data features describing input features describing the demographic information of our clients. For this second cluster, we're going to look specifically at product preferences, while the third cluster will have a combination of the two and see how well it performs in relationship to the previous two clusters. So moving on to the experimental results. First, we can see that the null accuracy is 63.71%. Null accuracy is pretty much a baseline model evaluation procedure, which describes the accuracy that could be achieved by always predicting the most frequent class. While it is not a useful model in itself, it provides a good baseline for the comparison of our experiment results. As we can see, the preferable approach for our problems would be the decision tree algorithms, doing the best performance on strictly taking product information as input features. Therefore, we can conclude that demographic information is not that relevant when predicting customer purchase behavior. Moving on, model evaluation metrics. Well, classification accuracy is the easiest classification metric to understand. It does not give us the insight of the underlying distribution of the response values. Additionally, classification accuracy does not show us the type of errors that our models are making. So we can approach this problem by using the confusion matrix. By using the confusion matrix, we can also provide new insights on the performance of our predictive models by calculating new evaluation metrics. For our example, we're going to look at each model individually. We can see that our models are mostly focused on are optimized for specificity, which describes when the actual value is negative, how often is the prediction correct, compared to the sensitivity, which is when the actual value is positive, how often is the prediction correct. Well, how can we determine which evaluation metrics should our models be optimized for? We're going to discuss now. The choice of our evaluation metrics should be determined strictly by our business objectives. So take, for example, a program that is a spam filter where the positive class value means fraud. This is where false negatives are more acceptable than false positives, meaning that we want to prioritize normal messages not getting sent to spam. Well, in our case, customers that are labeled as heavy spenders are the most potent to customize promotions. And therefore, we come to the conclusion that our model should be optimized for sensitivity, meaning that false positives are more acceptable than false negatives. For our next slide, we're going to...
Sorry, but time is pressing us, so yes. Can you go to the questions?
Yes, I have 3 more slides. Basically, I also discussed the importance of modifying the threshold value in order to optimize for our specified parameters. And in conclusion, demographic information is not as important as product preferences for customer when it comes to predicting customer purchase behavior, and decision tree learning algorithms are the most suitable for this problem. And this is it. Thank you. And if there are any questions.
Thank you very much. I would like to mention that this activity of client profiling is not quite legal in Europe. Based on GDPR, a given company can do this kind of activity only if it has the approval of the clients. And in most cases, this is not happening. There are a lot of law cases when big companies like Google, like Facebook had to pay a lot of taxes because of this kind of activity. What do you think about this?
So this is interesting because, first of all, well, when it comes to customized offers, users kind of want this feature because it provides a much more fluent purchasing experience, and therefore the companies can approach this problem by offering compensations for their data. So, for example, they can get a discount if they agree to the terms of customer profiling. And
the other problem with profiling is that for some products we buy once in 10 years. For instance, I am buying a refrigerator. Probably the next time I'm doing the same thing is in 10 years. So how can you separate products which are bought very often via products which usually, if you bought something at a given moment, you will not buy it in the near future?
So when recording the past behavior of a customer, we can also take account of the quantity of each product purchased, and therefore we can differentiate the products that are more purchased on a monthly basis compared to products that are purchased on a yearly basis. We just need to add this parameter to our data set as the amount of quantity of a set purchase.
Okay, thank you.
Thank you.
Thank you very much. I'm gonna share my screen right now. I hope you hear me. And you see my screen, right? Okay, thank you. Good morning, everybody. My name is Kishra Luca Diana, and today I'm going to present you my paper about analysis and prediction of stock market values, followed by a short demo. Why is it useful? Well, stock price analysis and prediction may help investors to gain knowledge from their data that otherwise may seem worthless. And with that, they can make informed decisions and prevent massive financial losses. How do we make that? In order to achieve our goal, we collected data from different resources and analyzed them through three different models that use different technologies. And last but not least, we designed an interactive and user-friendly interface. GameStop. Well, this is American video game merchandise that in the first half of the last year had a continuous decrease. And we choose to analyze the situation of this company since something very rare happened at the end of the year 2020. Users of the subreddit Wall Street Bets noticed that the company was undervalued by the big investors who bet on its decline, and they started influencing each other on this platform to buy options in order to raise the price, and they succeeded. For that reason, we were very curious to see if this movement could have been predicted. For the next few slides, I'm going to present you the data that we used. We had two main sources. One of them is Yahoo Finance, from where we took our financial data, and the other one is the subreddit Wall Street Bets, where people usually post messages related to stocks. Regarding the financial data, we choose to work with the period between the 1st of May 2020 and the 31st of March 2021, since we wanted to observe how the prices evolved before and after the movement that took place in January. After collecting the data, we pre-processed it a little, and in the end we worked with the closing price, the volume of transactions, and the date. One of the models we are going to present you later uses a sentiment analysis model, and for that model we used two datasets for training and testing. That datasets that contained short and compact messages classified as positive or negative. And for experiments, we collected posts from the Wall Street Bets subreddit. I already mentioned it. All the messages were first processed and then encoded with a pre-trained word embedding model named Glove. For the next few slides, I'm going to present you the models we used. The first one is based on a recurrent neural network, RNN, and you can see his architecture in this picture. The model contains a long short-term memory layer with 256 units and two other dense layers. Of all three models we developed, this one performed the best, obtaining a mean absolute percentage error of 0.56. We went a little bit further in our research and tried to improve the first model by adding an ARIMA algorithm, which is very well known for its flexibility and versatility. The first step was to decompose the data into trend and seasonal component with noise. Afterwards, we trained the ARIMA model with the trend data and the RNN model with the seasonal component. Predictions were made for each model, then the results were multiplied back together and the final predictions were obtained. With all our hard work, the error rate did not decrease, obtaining a MAPE of 0.65. Last but not least, the model that combines a neural network with a sentiment analysis model. This one is by far the most interesting since it makes use of the public's opinion when making predictions. For that, we built a sentiment analysis model that obtained an accuracy of 78% and whose architecture can be seen in this picture. After collecting the Reddit posts and classifying them with this model, we obtained daily values between 0 and 1, 0 meaning negative and 1 positive for the period of time I mentioned before. With these results, we enriched the financial data set and then retrained the RNN model, obtaining in the end a MAPE of 0.57, so very close to the first one, but not improved, unfortunately. For the future, there are a few things to be taken into consideration, and one of them would be to add some more financial indices, for example, the relative strength index or the number of Google hits related to the topic, and maybe use some more data for the sentiment analysis experiments we made, maybe from different resources. And now I'm going to present you a short demo of the application. This app has an intuitive and easy to use UI and is divided into 3 sections: Home, About GameStop, and About Wall Street Bets. The first one, Home, contains financial representations of data using different time slots. All the graphics are interactive, so the user can go around, look for prices, has access to the trend of the data, And this graphic represents the historical prices, the real prices, and how our best model predicted the prices. Then also in this section, there are 3 graphs about the sentiment analysis experiments we've made. In this graph, the user may easily notice that beginning with December 2020, the interest in the GameStop company increased a lot. So the number of daily messages increased, and there were people considering having negative opinions and other positive, but in general there were more positive than neutral and negative. The second section exposes the results of our research, and I'm going to come back to this immediately. And the third section is about Wall Street bets in order to give the users a little perspective on the data we used for sentiment analysis. Well, this graphic is by far the most interesting because at first it presents the historical price, and it's very easy to notice that the prices fluctuate between $4 and $16. Our hybrid model predicted that the price will go up to $53 in January. Then the model with sentiment analysis predicted even higher prices with a maximum of $85 and with more fluctuations. And the closest one to reality, the recurrent neural network alone, predicted a maximum of $92 also in January. All these predictions are very good, but the real price was in fact even bigger with a maximum of $347. But of course, these increases and decreases were very short, which made them very hard to be predicted. We are very proud that our models managed to intuit market fluctuations, although not at their true magnitude. It is also very important to mention that all these models perform a lot better on more stable data sets, where the stock prices do not fluctuate that much on a daily basis. But our purpose was to predict the unpredictable market movements, and we think that we made one step further into achieving this goal. That was my presentation. Thank you. Well, the financial data set contained around 232 data after preprocessing it. During the preprocessing, I eliminated some tuples that contain 0 values for the closing price. And the one for sentiment analysis contained around 1,600,000 messages for training and testing. Well, the financial data set didn't take very much time to train and to test, but the sentiment analysis model took more than 10 hours to be trained, and then all the experiments took somewhere around 180 hours, so a lot of time.
Yes, this show me what I also already know, that stock market is like gambling on sports, Sometimes you know some inside information and you may win a lot of money, but if you are an outsider and you don't know these inner informations, then you are losing. Another colleague of mine who was working on programs for stock market said that on short term, the small players may win some money, but on long term, all the small players are losing because they don't know the essential information which changed the market. So those big companies who invested for a short period of time in this company, GameStop, I think, knew that for a short period of time the market will be very high. But they also knew that this is an artificial increase. But anyway, it is good that there are efforts to try to understand these movements and try to predict, and the small investors can use such tools in order to be more informed. Thank you. If you agree, I would like to present the next student. Alina Shomkutean. She will present us something about stars. Stars, I think, on the sky. I also would like to present Delia Mitria, who will take my place in this session. Unfortunately, I have to be part in another meeting, so bye-bye and
hello, I am ready, so
okay.
Okay.
So you are present. So Alina Shomkutean, please do your presentation.
Hello. Can you hear me well?
Yes.
Okay.
And also see your presentation.
Okay, just a second. Okay, so hello, my name is Alina Shomkutean, and I'm a student at Computer Science. And today I am going to talk about a project which combines the main two passions of mine, technology and astronomy. I will start by describing a little bit my project and present to you the project objectives. Then I will speak about each representative part from my project, starting from the bibliographic research I did at the beginning to design and concrete implementation of the application. First of all, probably most of you already know that a constellation is a group of stars. According to International Astronomical Union, the sky is divided into 88 areas, which corresponds to 88 constellations. Even from a long time ago, people were very interested about the sky and started to imagine that stars are connected between them and form specific things, starting from common objects to the most varied animals. This was only the beginning because humans created myths and stories about each constellation. Moreover, people used them in order to orient themselves and even determine time. My project can be considered an atlas of the sky, since it contains a lot of information from this domain. It is also a web application for familiarizing with a new domain, astronomy, and it can be used by anyone. The main objectives for my project are the following: detecting the constellations from an input image and present details about astronomical objects. Now, continuing with the bibliographic research, there are many factors which affect the way in which we see the sky and, as consequence, the constellations which are seeing. The most important one is your position on the Earth. As you already know, the Earth is separated into two hemispheres. This separation is very important because due to it, there are some constellations which can be seen only from an hemisphere. For example, we from Romania will not be able never to see Centaurus. Moving forward, movement around the axis has also a big impact about the way we see the sky, because we will need to go out at a specific hour to see Leo constellations, for example, only after it rises. But going out at the same hour every day, it doesn't mean that we see the sky exactly the same, because there are constellations which we can see only in some periods of the year. For example, Orion constellation is specific to the winter sky, and it cannot be visible in this period. In order to work with real data regarding the astronomical object, I started by reading and understanding the SINBAD database provided by Max Planck Institute for Astronomy. This data is separated into 3 categories: basic data, which contains objects like galaxies, planets, coordinates, velocity, and so on; cross-identification, which basically contains allies for objects; and observational data, like distances measured, magnitudes, and periods. Regarding the related work, there are 3 similar softwares. First one is Stellarium, which provides the chance of seeing the sky in the same way as it can be seen with the naked eye, and also by zooming it, it can show you the astronomical objects from a closer view, similar with how they would appear by looking through a binocular or a telescope. Also, it offers the possibility to set your actual location on Earth and time. Then Google Sky. This tool offers you the possibility to look at the sky in different wavelengths, like infrared or microwave. Comparing with the Stellarium software, this one provides real images of a selected object. And the last one, Heavens Above. Besides the other 2 presented, this tool provides the option to see all the currently visible satellites and their trajectory. Now let's move further to the analysis and design step. This is the architecture diagram of my project. As you can see, it is a client-server application. The client makes a request to the REST API services, and the server receives the request, processes it, and sends back to the client the response. Also, the image processing application can be an intermediate between client and server for the constellation detection feature, but I'll provide more details about this part later. Also, as you can see, the server is designed using the model view controller architecture. On this slide, the languages used for each application are specified. For the image processing side, I choose to work with Python and OpenCV. On the server side, I am working with Java and Spring Framework, and there's a database PostgreSQL. And for the client side, I use React, JavaScript, and Bootstrap framework. This is the main use case diagram. As you can see, there are 2 types of users, admin and regular user, and they both need to be authenticated in order to access the application. Now, let's move forward to more interesting things regarding the implementation details. The first thing done in realizing my project was to implement the database using PostgreSQL. As I already mentioned, this database was needed in order to provide additional information about astronomical objects. Since there are many types of astronomical objects, I choose to classify them in order to have a more simpler and easy to understand database. And some of the categories are simple, compound, extended, messier objects, and also solar system, which contains planets, asteroids, comets, and so on. This is my database diagram, where you can see how I connected all the categories mentioned before, and also some other categories for a more generic database. And now image processing is the main part of my project. That's why here more steps were needed in order to implement it. The first step was creating the templates. The templates are actually a set of images with all the constellations taken from the International Astronomical Union, but much more simplified. So in the end, the template used contains only two colors, black, which represents a background pixel, and white, which represents a star pixel. Each constellation has more stars, but the magnitude of them is different, so I need to know the brightness of each star. For this, the area of each star is computed. This area is actually the number of pixels for each star. But because initially all the stars have the same color, a labeling algorithm is applied before, resulting into coloring each individual star into a different color, making the computation of area now easier. But knowing the brightness of star is not sufficient for detecting the constellations, so the distance between the brightest star and all other stars is computing using the formula for the distance between 2 points. Next, the angle formed by the imaginary line, which represents the distance, and the OX axis must be calculated. All the computed data is saved into an external file in order to avoid the option of computing the same things many times. Here is presented an example of a template. The constellation presented here is Ursa Major, and in figure 1 is the template in a binary form, while in the second figure, the constellation is shown after applying the labeling algorithm. After having all the templates and the information saved into an external file, the next step was to preprocess the image provided by the user. Since the picture can be done in many ways and many other objects like buildings or trees may be presented in the picture, the first thing done here was to transform it into a binary one in order to eliminate them. Also, I had to take care of the size of the image, which can be very different from user to user. That's why I use the standard size, which is the same with the template. Here is also presented an example of an image before and after the preprocessing. In the picture from the left corner is shown the initial image, exactly how it was taken by the user, while in the one from the right corner,
sorry, I cannot hear you anymore. So take care to your microphone. Maybe it has been closed. It has been shut down. Okay. So what can we do now? Okay, we will call her by phone. No. Alina, can you hear us? Nu știu, sună mai bine.
and which means that the area is the same. You still can hear me, right? Okay, so here. Okay, I will retake it. Is it okay? Okay, so here I said that this is the most important part from the image processing, because here I actually do the detection constellation. And after I had the picture preprocessed, as I already mentioned previously, similarly in the case of templates, I apply a labeling algorithm in order to have each star colored differently and making the computation of area more easier. Area is computed again by counting the number of pixels with the same color. In order to determine the brightest two stars, this area are sorting in a descending order, and the first two stars are picked. For each of the two selected stars, I suppose that it is the brightest star in each template, and go to the template set. Suppose that the brightest star from the template is the same with the selected star from the image, and This means that these areas should be the same. Because the users can zoom in or out in order to take the picture, a scale factor should be computed. Supposing that the assumption made before is true, the scale factor is computed using this formula by dividing the area of the brightest star in the test image and the area of the brightest star in the template. Now I will explain better the reason why I need to compute the distance and the angle in templates, considering the assumption made before true, and I check the existence of the other stars by finding the distance at which another star should be found in the test image based on the distance computing in template and the scale factor. But since the provided image can be rotated in any way, in order to reduce the possibilities, the angle is used. So having the distance and the angles, we should know exactly where the star should be. The same thing is done for all other stars in constellations. If at least half of the stars were found, then the constellation is considered detected. I put this condition because in pictures can be part of the constellation missing, so yeah. Now with the constellation detected, I move forward to implement the server in order to provide additional information about what was found in the pictures, and also some extra features like authentication, possibility of being up to date with the events and news from astronomy, and also the ability to subscribe to a newsletter for receiving the upcoming events in which you are interested. Since the authentication is needed, also minimum security is needed. For this, JSON Web Token method was used. In this method, the token is stored in the client side in local storage, unlike other methods which stores it into cookies in browser. This approach offers also the possibility to extend my application in a mobile one later. Moving forward to the client side, this one was also an important step in realizing my project since it creates the first impression to the user. Also, I wanted to provide a design specific to the team and make sure that some common errors which can come from the users are prevented. And now references. Here are the most important references mentioned in my project and in these presentations also. Thank you. If you have any questions.
Okay, so what data did you store in your database and with what purpose?
Data about constellations, stars. In order, when I detect the constellations, I send that constellations to the server, and server gives back to the user all the information about the constellations. That means that constellation Ursa Major, for example, it has these stars, this magnitude, it has this story, and so on.
Okay, thank you. Other questions? Of course. Thank you, Alina.
Yes, good morning. I hope you can hear me and actually see my screen. So my name is Răzvan Zoltan. I'm a computer science student at Babes University of Cluj-Napoca, and my study involves Romanian Sign Language recognition using one-shot learning. So we should begin with what actually are sign languages, because humans generally use spoken languages and spoken vocabulary to communicate. So that would be pretty much of a challenge for the hearing and speech impaired communities. So sign languages appear to improve this experience of communication. And they can also be considered standalone languages, having syntax, grammar, and standalone vocabulary. And as a problem involving sign language, we can consider the sign language recognition problem. And as technology advanced more and more throughout the years, the automation of sign language recognition has become possible. And the reason behind this is that they have a well-defined structure and they can use as a testing support concerning, for example, computer vision algorithms. And the whole recognition process involves registering and recognizing visual and manual cues by different methods. Some researchers chose image methods, as in image processing, video methods, as in video processing, and sensor methods by examining some signals produced by some wearable devices and others. And as related work, I chose 2 papers which have treated this concept. For example, the first paper written by Al-Zohairi and the other authors treated Arabic Sign Language recognition. They have used the support vector machine classifier and texture descriptors for the skin representation. And they have obtained an overall accuracy of about 64%. And another computer vision paper which treats this concept is written by Tolentino et al., which treated American Sign Language recognition and used just a convolutional neural network architecture, and they have obtained an overall accuracy of about 90%. So about the technique I use for this process, about one-shot learning. When one wants to use deep learning techniques to train models, we usually need large and extensive data sets to train them. So this technique, one-shot learning, solves the need of enormous databases. And the way it works is very similar to how humans, and especially children, learn concepts when presented a very limited number of examples. And why is it called one-shot? Because it is needed only one, for example, look, that means training example, to perform further recognition. And some learning architectures in which one-shot learning can be used and can be further implemented are, I have selected 2 of them. The Siamese neural networks, which take 2 identical neural networks, usually convolutional ones. Then the feature vectors produced by them are conjoined, and there's a distance computed. And then we reach the target. I will insist on this kind of architecture more in the further slides concerning my proposed model. And also the triplet loss function method, which involves this time 3 networks and 3 kinds of inputs: the anchor image and the positive image, which both are considered to be very similar, and the negative image, which is considered to represent a whole another thing than the other 2. And the triplet loss function basically minimizes the distance between the anchor image and a positive image, rather than an anchor image and the negative image, as you can see in the diagram. A very important contribution to this study was the data acquisition process, meaning that considering the lack of data sets, according to our knowledge, concerning Romanian Sign Language, I have decided to create my own data set by taking pictures of volunteers. The data set originally contains around 50 images per class, and there are 26 classes in total, which consist of all Romanian letters excepting J, Sh, C, and Z, because they require continuous motions, and this study involves only static image recognition. Then it's pre-processed by resizing from a pretty large resolution to 2 to 4 times 2 to 4 pixels, and also converting them to grayscale because we are more interested in the shape of the hand and on the position rather than colors and skin color and such. Also, the dataset was enriched using image augmentation. As you can see in the diagram below, all the images were flipped, zoomed, and both zoomed and flipped in order to construct a larger dataset, precisely 4 times bigger than the original one. And the dataset was converted into image pairs, which were labeled as similar or non-similar, as in if they represent the same depicted sign or not. So my proposed model is a Siamese neural network architecture, which consists of a twin convolutional neural networks with shared weights, which involve convolutional and max pooling layer for bringing the best out of the images, the most relevant features, and also emphasizing them, and also batch normalization layers for regularization purposes, for speeding up the process of learning and to prevent overfitting. And as you can see, after the feature detection pipeline, the feature detection module, 2 feature vectors are obtained, and these 2 feature vectors are conjoined, and there is performed an absolute distance between the 2 vectors, and then we have a single layer, a sigmoid activated layer with one unit, which will represent a floating point number between 0 and 1, which will mean further the similarity degree of the 2 images which are fed into the model. Further on, for the training phase, my model was trained for 100 epochs and on approximately 8,700 image pairs with a batch size of 16. And as you can see in the plot and in the slide, the accuracy amounted around 98, pretty close to 99%. And my training loss amounted to approximately 0.2, which, as you can see in the plot, is a pretty good performance as it is almost tangent to the x-axis of the graph. Concerning the testing phase, my overall testing accuracy was around 80%. And out of all non-similar image pairs, as you can see in the first table, 97% of them were predicted correctly, which is a great recall performance. And I have also obtained a 96% precision for similar image pairs. However, my model predicted a fair amount of non-similar pairs as being similar, so that amounted a 64% recall. And the reason behind this, the possible reasons behind this issue could be either the feature detection phase, the CNN twin network, the quality of the dataset, or the number of images or data pairs. So to conclude about the study, and first I will present you a quick demo of a support application. My study involved the development of a Siamese neural network architecture. The most important contribution was the dataset, which was built from scratch. The training accuracy was around 98.71%, and the testing accuracy was around 80%. And the possibilities of further improvement were I could possibly improve this study by adjusting and enriching the dataset more, maybe approaching the triplet loss function method, performing continuous image analysis, as in treating videos and not images, and could also perform word level recognition instead of a letter level recognition. Moving on to the demo. For example, we would like to see how some photo would be predicted. And there is presented for each of the classes a similarity degree, meaning how much it resembles the specified letter. For example, this is letter A. And the way I do the prediction is that I have support set of 26 images, and the given image and each of the images in the support set are fed into the model, and the similarity is computed. And as another example, corresponding to letter in Romanian, and as you can see, it is recognized as being 87% of letter A. So this is my presentation, my study. I want to thank you for your attention, and I'm open to any questions you have. Yes. I have used TensorFlow and Keras as backend frameworks in Python in order to implement the model, but the architecture is, I have also tried another architectures, but they haven't performed that well. So the only thing I have used, which was already implemented, are the implementations of the layers. Okay. So basically, I have compared them with specifically one paper from the literature, and they were pretty close, but their approach was a bit better, but they were pretty close. But they especially used a much larger data set and a simple CNN architecture. So the training was done on around 8,700 image pairs, and it didn't take that long because of the size, but I have performed a lot of experiments and tried to refine the architecture in order to obtain favorable results. Thank you.
I don't have questions right now. I propose to switch to the next presenter as we are a little bit late. So I will present Beatrice Andrea Morginean. She will sustain the presentation with the title Predicting Age-Related Macular Degeneration Evolution from OCT Scans. So Beatrice, are you prepared?
Yes, hello. I will share my screen in a moment.
Of course.
Do you see my screen?
Yes, yes.
Okay, so I'm Andrea Morginean. I'm a student at the Technical University of Cluj-Napoca, and today I will be talking about predicting AMD evolution from OCT scans. To begin with, this research project is rooted in a medical domain problem, so I will start with a short introduction regarding the medical context. Optical coherence tomography, OCT, is the leading imaging technology capable of helping ophthalmologists in diagnosing various retinal conditions. And there are several types of OCT scans, but in this presentation we will focus on the OCT fundus scans. As we can see here in this image, AMD is one retinal disease that can be diagnosed by analyzing the OCT scans, where the ophthalmologist actually is able to observe multiple biomarkers that indicate the disease evolution. For this research project, we similarly used the OCT volumes in our data set. The data set consists in a time series of doctor visits for 94 patients suffering from AMD. And besides the images, we also have numerical values, which consist in retinal thickness and volume values from all the 9 zones that can be seen in the image A. And also for each visit of each patient, we have visual acuity measurements and a variable specifying whether treatment was received at the visit or not. So the main purpose is to predict the AMD evolution, specifically to predict the evolution of the visual acuity, which is the main indicator of the disease evolution. Such a software could be a huge opportunity to provide help to ophthalmologists, such that they will be able to analyze faster the evolution of the disease in order to provide early treatment to their patients and prevent the irreversible blindness effects of the disease. And the main objectives of our solution is to handle the irregular time series of varying sizes from our data set, and to use OCT features from OCT images in order to forecast future visual acuities. Regarding existing solutions for predicting age-related macular degeneration evolution, we can see that multiple machine learning algorithms can be used, from linear regression to ensemble methods such as random forest or gradient boosting, up to deep learning. We can see, for example, in paper 4 that deep learning was capable of achieving higher performances. And similar to our solution, LSTM network, long short-term memory network, perform better compared to classical machine learning algorithms. And moreover, OCT fundus images have been shown to improve prediction results, and based on the proposed solution by Waldstein et al., an autoencoder was used to extract the features from the OCT fundus images. And regarding the data processing, which is an important step in this project, data cleaning was first of all performed by removing the sequences with only one visit, or by removing the data that had missing values that cannot be replaced. Otherwise, linear interpolation was used to replace the missing data. We also had to consider to handle the irregular time intervals between the doctor visits, and scaling was used to scale the data between 0 and 1. And moreover, a convolutional autoencoder was used to extract the most relevant features from the OCT images, and considering a small data set, we performed augmentation as well. Regarding the irregular time intervals, we considered two approaches. In the first one, we predict the future visual acuities for the next visit based on the previous visits, but in this case, we need to have equal time intervals. So time series resampling is performed to transform the frequency of the visits such that they are equal intervals. And similar to this image, we obtained equal time intervals, but in our case, we used 1 month as an interval. In the second approach, which didn't work as well,
The original time series were used without any changes, but we also included the timestamp of each visit as an input feature. And also the time span that was needed to forecast the next visual acuity for. And in this image, we can see an example on how we computed the timestamp feature for each visit, which is represented in the number of months from the first visit in the sequence. For extracting the most relevant features from the OCT scans and thus reducing the dimensions of the images, we have used the convolutional autoencoder, which is actually a neural network that consists of an encoder and a decoder part, where as you can see in the image on the slide, the encoder is capable of obtaining latent space representation of the image, and based on that, during the training, the decoder learns to reconstruct the image. According to principal component analysis, we use the latent embeddings of size 256 that can cover a decent amount of the overall data variance. And the autoencoder obtained the mean squared error of 0.007, which we can see in this actual image reconstruction that it worked pretty well. Regarding the time series augmentation, considering the small data set and also considering the fact that the time series have a different number of medical observations, the overlapping sliding window augmentation segmentation was performed, which consisted in applying a window of size k on each time series, thus generating more time series of size k. An overlap equal to 1 visit was used, and we can see here in this example that from a sequence of 5 visits, 3 visits were generated. And after the previous pre-processing steps, 115 time series were obtained, which were then augmented, obtaining the numbers for each scenario as here in this table. Regarding the experiments, we have 4 main experiments for predicting future visual acuities based on the input data. So these experiments mainly differ from the input data that was used. And also for each experiment, we considered both approaches for handling the irregular time intervals. And for each experiment, time series of size 1, 2, actually with 1, 2, and 3 previous visits were generated. To be noted that the treatment feature was used in all experiments. Experiment 1 focuses on predicting future visual acuities from previous visual acuity measurements. In experiment 2, we have used the numerical values from the 9 zones of the retina. In experiment 3, we also included the image embeddings of size 256. And in the last experiment, all data from the previous visits was used to predict the visual acuity for the next visit. Regarding the algorithms used, machine learning algorithms were employed. However, the focus was on deep recurrent neural networks. And we can see in the image the architecture of the proposed LSTM network, long short-term memory network. The other networks, the simple RNN network and the gated recurrent unit network, were also similar. The only difference being that in the second layer we have used, instead of an LSTM, a simple RNN layer, respectively a gated recurrent unit. And based on the overall forecasting results, we can see that when using all data, the higher performances were achieved. This is in experiment 4. And moreover, it can be observed that when additionally using the images, the results were improved in experiment 4 compared to the third experiment when only numerical values were used. And when using only 2 features in the first experiment, linear regression performed the best, but overall deep learning achieved higher performances, specifically the LSTM network. And we can see that the LSTM network performed the best in the case of resampled time series with 3 previous visits when using all input data. And here we can see the actual predictions of the best LSTM on the test data. We can observe that the predicted visual acuities are highly correlated to the actual visual acuities, indicating also low prediction errors. And in order to test the overall efficiency of the LSTM network, a tenfold cross validation was as well applied for a better estimation of the performance on our data set. And we can once again see that resampling achieved higher performances, including the images also has shown significantly better results. And overall, using all the input features was the best, achieving a cross-validated score, R-squared score of approximately 0.96. So in conclusion, we have determined that the OCT scans are indeed predictive of the AMD evolution, and using an autoencoder to extract the relevant features from the images significantly improved the forecasting results. And moreover, deep learning performed the best, especially the proposed LSTM network. And the irregular time series problem was also solved using resampling, and thus it also led to better predictions. Regarding further development, we can also improve the results from that in the scenarios that weren't the best. We can also try to predict other things, future images or future numerical values, not only the visual acuities. And we can also perform tests for other retinal diseases evolutions. But the main further development focus would be to explain the LSTM predictions using interpretability or explainability tools in order to enable the ophthalmologists to understand the predictions that were made by the model, and therefore to understand what were the most important features that led to the prediction. And here is the bibliography I have mentioned in the presentation. And thank you for your attention. If you have any questions.
Can you tell us what is the relation between the autoencoder and principal component analysis?
Yes, well, I have used the principal component analysis in order to compute the explained cumulative variance of the overall data set in order to determine how many components are needed in order to obtain specific percentages of the data variance. So by using the elbow method, I have computed a plot with this cumulative variance on the overall data set, and the most reasonable size to be used was 256 for 80% of the data variance.
Okay, but you actually applied both PCA and autoencoder, or only the autoencoder according to this variance?
Only the autoencoder according to the variance.
Okay, so somehow the autoencoder resembles a PCA.
Yes, I have read many papers, research papers that have shown that PCA can be used to obtain the number of components, but better performances can be achieved through autoencoders.
Okay, okay, thank you. Are there any other questions? Okay, thank you, Andrea, then.
Thank you.
Yes, hello. 1 second. Yes, now I think. Do you see my screen? Okay. So my study revolves around presenting an approach to augmented reality content superimposition in a mobile environment, achieved through analyzing human body structure and using close overlapping methods. The current pandemic emphasizes the importance of having accessible, easy-to-use online tools such that physical presence can be avoided for certain activities. One of the obstacles of easily migrating into the online environment are the technical limitations regarding things like food tasting or trying on clothes. Not only is moving the online environment an
I cannot hear Theodora either. Okay, freezing the screen, maybe some network issue. Can we contact her somehow? Okay. Can't we contact her via chat or something?
Yes, do you hear me? I had
it's okay
problems
now.
with the internet connection. I'm sorry.
Again, there is some freezing.
Oh, okay. Can I turn off my camera or okay. Okay. So yes. So the current pandemic emphasizes the importance of having accessible, easy to use online tools such that physical presence can be avoided for certain activities. One of the obstacles of easily migrating into the online environment are the technical limitations regarding things like food tasting, trying on clothes. Not only is moving into the online environment an important thing, but there are also visible advantages to providing a system using augmented reality technology. So the presented approach is an on-device real-time system of clothing overlapping. There are two main aims in addition articles, which result in a better and modular way of overlapping the clothes. Even though the whole process of the proposed system is real-time, the pose estimation is image-based, which favors the use of a CNN. There are multiple ways and implementation for this problem, but for the pose estimation and detection itself, I used Google's ML from the pose detection API, holds positional information with which geometrical calculations are done to fit the clothing objects. Sorry, do you hear me? Okay. Okay. Yes, sorry. There can be different ways of handling the fitting process, but the main idea which was implemented consists of segmenting the clothing objects and overlapping them based on their respective body parts. So the clothing articles are meant to be one cohesive object captured in a single image, which is then segmented into different parts according to certain heuristics. The process of splitting the clothing object into smaller segment images is done manually, and all segments are then associated with that clothing article. In the current implementation, every clothing do you hear me? One second, I will switch my internet. 1 second.
Okay, we can try. We can try to introduce the next one then. So Andrea Prikop, predicting the geo-effectiveness of CMEs using machine learning. Andrea Prikop, are you prepared?
Yes, can you see and hear me well?
Yes, I can see the slide, I can hear you, and I can see your camera. You can start.
All right. Honorable jury, distinguished guests, and dear colleagues. My name is Andrea Pricopi, and today I'm going to present you my study on the use of machine learning methods for predicting the geo-effectiveness of CMEs. First, I'm going to introduce the terminology and the motivation behind this study. Then I'm going to present the data and the reason why this task is not a trivial one, after which I'm going to describe my experiments together with the results and comparisons with their previous work, and leave you with some conclusions. Let us first understand what the CME is. CME stands for coronal mass ejection, which is a powerful explosion from the sun's atmosphere that is known as the corona, that looks similar to what you can see in the lower right corner of this presentation. This right here is an actual coronal mass ejection. And this explosion basically sends billions of magnetically charged particles of solar plasma through the universe that sometimes, under certain circumstances that are not completely clear for us yet, can reach and affect our planet. And the way a coronal mass ejection reaching Earth is affecting us is by disturbing and weakening our magnetic field, which looks similar to what you can see in this animation and is called a geomagnetic storm, while the capability of an event to create such a storm is called geo-effectiveness. But why would we want to predict the occurrence of such a storm? Well, this basically is rooted into the effects of such a storm. And the one you can see here is the most beautiful effect of a coronal mass ejection, which is the spectacular light show known as auroras in the polar regions. However, this is also the most inoffensive effect, and the real reason we're actually studying geo-effectivity is because of its negative potential effects. Many of you probably know already that electricity is primarily based on electromagnetism, and such a storm would basically induce new currents into our grids that could lead to potential electrical failures, transistor failures, and even blackouts. Also, navigation and positioning system could have errors of tens of meters due to the fact that the trajectory of the way the signal propagates from and to the satellites in the ionosphere would be disturbed due to the interaction between the solar particles and our ionosphere. This is also the reason why radio communications and radio frequencies would be affected, and the main actor that would be affected by this would be the segment of aviation, because pilots use radio frequency to keep contact with ground control. Another dangerous effect would be for astronauts who are on space missions and outside of their shuttles to be exposed to way higher levels of radiation than usual. So we've now understood why we need to predict these geomagnetic storms, but how do we know when there's a geomagnetic storm occurring? Well, we could basically look at one of the geomagnetic indexes, like DST, that stands for disturbance storm time. So this is basically an index that tells us that if its value drops below -30, there's a geomagnetic storm happening at the moment. At the moment, researchers and scientists around the globe are monitoring data from our solar missions and the satellites in our orbit 24/7 in order to forecast solar weather and warn affected agents on time. Of course, in the recent years, there has been more interest into using machine learning for this task. However, using machine learning for predicting geo-effectiveness is still in its infancy. But the fact that there are still unanswered questions about what makes a CME geo-effective leads us to believe that maybe machine learning could help us get some more answers. So what I decided to do is build and compare 4 binary classifiers that would help us decide and predict whether coronal mass ejection will be geo-effective, meaning it will be associated with a DST value lower than or equal to -30, using only solar parameters, because this offers us the longest warning time. In order to this, I have collaborated and communicated with 2 domain specialists in order to better understand the domain and the data. And then I've started building my data set, which contains solar data from the main solar NASA mission called SOHO. Then I've correlated the CMEs with the DST values from the catalog that is considered by domain specialists to be the official association between geomagnetic storm and their causes. And I've also added a new index, a solar index that basically gives us some information about other solar phenomena called solar flares. Analyzing the data, I saw that thankfully and fortunately for us humans, the vast majority of coronal mass ejections since the beginning of the NASA mission have not been geo-effective. Actually, over 99% of them have not been geo-effective. Unfortunately, for machines, this is not good news because this means that our data set is extremely imbalanced. Another problem is that we have few parameters available at the moment. And there's also the problem of observed geomagnetic storms that are not yet correlated with the cause. This is because there are other solar phenomena that could be geo-effective, and it can also be due to the fact that CMEs take from a number of hours to a number of days to reach Earth. So in a time span of a couple of days, there could be multiple coronal mass ejections that could potentially be geo-effective. And since scientists cannot know which particular one caused a geomagnetic storm, all coronal mass ejections from that time span are actually considered to not be geo-effective. For my experiments, I chose to build and compare 4 models that are K-nearest neighbors, support vector machines, artificial neural networks, and autoencoders. However, besides their default implementation, I've realized that in order to overcome the challenges I've just presented, I would have to use some optimizations. And in the following moments, I will describe briefly the most interesting or most relevant ones. In order to help most of my models to not predict only the majority class, I had to use balanced class weights, which basically mean give more importance to the minority class, which is the class of geo-effective coronal mass ejections, and penalize the model more when it makes mistakes on those examples at training. I have also tried to synthetically create new new events that are geo-effective by using the SMOTE technique to upsample the minority class. And while this led to significantly improved results at training and validation, when tested on real data only, the results were very similar to those of the models that were also trained on real data only. I have also tried to look at the problem from a different perspective. I've thought that since less than 1% of the events were geo-effective, maybe they could be considered anomalies. And in this case, we could use an autoencoder to detect them. As you have already heard, autoencoders are special neural networks that basically can reproduce the data in a simplified, meaningful way. So due to this simplification, we obviously lose some of the information, and that means that we have a reconstruction error. The way an autoencoder can tell us whether we're seeing anomalous data is by looking at this anomalous error. If this reconstruction error, if the reconstruction error is higher than the usual, it is we're most probably looking at an anomaly. And with this approach, I got very good recall values, however, very poor precision, which led us to believe that maybe looking at geoeffective CMEs as anomalies is not the answer, or maybe there's something else anomalous there. In order to tackle the problem of potentially geoeffective events, I've looked at all the geomagnetic storms that are not yet associated with the cause, and I've associated half the weight of a geoeffective event to all the CMEs up to 5 days prior to those storms. And for the neural network, for example, I got better recall values than compared to using balanced class weights only. My best true positive rate, or the recall, or also known as sensitivity value so far, is obtained with the neural network having a single neuron. And I am correctly labeling almost 74% of the geoeffective data, while correctly identifying almost all non-geoeffective events. The best precision was obtained using k-nearest neighbors approach. However, this in turn has a very low sensitivity. Compared to other previous studies, the results of the neural network seem promising. And this is in the context of previous studies using more parameters and more data. That is because solar scientists computed by themselves additional variables than those publicly available, but also only used a subset of data. So they also have a lower number of CMEs and therefore geoeffective CMEs in their data sets, while also having more variables. And there are also approaches that are using interplanetary inputs as well, which leads to better recall values. However, this gives us less warning times because by the time we have this interplanetary information, the CME is probably too close to our planet. In the following slides, I will show you a visual representation in 2D of my prediction, colored by their prediction type label. I have used a dimension reduction technique called UMAP in order to get my data to be in 2D for this visualization. And here you can see all the correctly predicted negative values. Therefore, all the CMEs that were correctly identified as not being geoeffective, while here you can see the correctly identified geoeffective CMEs in green, the false alarms in yellows, and I would like you to observe that they're following some sort of a similar pattern as the green ones. And in red, you can see all the geoeffective CMEs that were not identified. From a solar perspective, I was saying that the results are looking good because it is the true positive rate that is the most important value for us, which is pretty high. And that is because of the cost of not identifying a geoeffective event. So we care more about identifying most of the events than not getting false alarms. And if you looked at the plot in the previous slide, you can see that the majority of my false alarms are similar to some of the correctly identified geoeffective ones. And that is because they're all coming from a special type of coronal mass ejection called CMEs that from a physical point of view are also the ones that are expected to be the most geoeffective or geoeffective in most of the cases. So this complies with the current knowledge on the matter. In the future, I would like to raise my precision value while not affecting the recall value, and I would hopefully get that by building a custom ensemble model using at least a model that has high precision value and one that has high recall value. And I would also like to see whether adding new information regarding the position of the originating source of the CME could give us better results. And that is because at the moment, there is no parameter that gives us, that tells us whether the CME comes from a part of the sun that is facing Earth at the moment, which I believe could lower my false alarm rate. This being said, Thank you for your attention, and I would very gladly answer any questions you might have.
Okay, so how can you explain that those huge differences between the true positive rate and precision in some situations?
This basically comes primarily from the fact that the data is so highly imbalanced, and the fact that I am penalizing the model more when it's making mistakes on geo-effective events, and the fact that I'm giving them more importance makes the model learn more of the features that makes a CME geo-effective and finds more resemblance between those events. So it tends to predict more events as being geo-effective. What I was saying as well is that there are very similar events in the data sets, some that are geo-effective and some that aren't. And one piece of information that could probably help lower the rate of false alarm is knowing whether the CME comes from a part of the sun that is facing us. By analyzing the images, scientists can tell whether the CME comes from a side of the Earth that is directed to us and therefore has more chances of being geo-effective than my model knows, because my model cannot tell whether it's coming from the other side of the sun. So what I'm saying is that despite the low precision value, the models could still be used for detecting potential geo-effective events and maybe take them through a human filter after that could see also whether the CME is directed towards us. And I could also improve that by maybe using images as well in the future and seeing whether the CME originates from a place that is directed to us. I hope that makes sense.
Okay, thank you. Other questions? Okay.
Hello, can you see and hear me? Okay, I'll try to speak a bit louder then. Okay, let me share my screen too. Just one moment. Okay, please tell me when you can see my screen. Thank you. So, hello everyone, my name is Miruna, and today I would like to talk to you about an application that I developed that, as the title says, deals with detecting interactions between pediatric drugs. But first, what are actually drug interactions and how do they occur? Well, anytime you take several medications together or combine a drug with certain foods or beverages, or even take a drug while suffering from some underlying medical condition, you run the risk of developing adverse reactions. And this could mean either a decrease or even increase in the action of the drugs you are taking, or adverse side effects, which in some cases could be even life-threatening. So, the information presently available to doctors and pharmacists in Romania regarding these interactions can be found in a rather unstructured form on the website of the National Agency for Medicines and Medical Devices in Romania. And this form is, as can be seen here, that of a table with a couple thousands of drugs that are presently available on the market in Romania. And for each of these drugs in the table, one can choose to download a document called Summary of Product Characteristics. And this is a PDF file of around 10 pages of information that is specifically intended for medical professionals. The information regarding the interactions, contraindications, and warnings, and that kind of information is mainly present in 4 of the chapters of those documents. But that is still quite a lot of information for the doctors and pharmacists to go through. Now, a bit on the technical side, the information was gathered from the website using Selenium, that is a framework for that can be used for web scraping. The text from the documents was extracted using a library called PDF Miner, and the chapters needed further on were extracting using pure Python magic, so to say. Now, for the solution to extracting the actual drug interactions from the plain text, the first step was a process called named entity recognition, and this seeks to locate and classify entities of predefined categories mentioned in unstructured text. And the named entities that I defined for this task were, as can be seen down below, drug or active substance, because these two are usually highly correlated, drug type, and disorder or symptom, which again are closely related. This was done using a neural network implemented using the SPACY library. The next step would naturally be to trace back these entities found in the plain text to entities in a database in what is formally known as named entity disambiguation. So what we can see here on the right-hand side is that there are 2 different entities labeled as A2 that should be traced, that would correspond to the same entity in the database. So that's what we need to solve. And the solution to this involves what is known as the minimum added distance, which offers a measure of a similarity between 2 strings by calculating how many operations you need to transform one string into the other. And the variation that of this algorithm that I used was the Levenstein distance, and the result was that I could link the entities in the text to their closest match in the database. Having done these prerequisite steps, we can now introduce the interaction detection problem as a binary classification, where for each small piece of text in the documents, we would classify it as being of either class 1 when the text refers to interactions, or 0 otherwise. And this was implemented using an LSTM network, whose architecture can be seen on the right-hand side of my screen, with the help of the Keras library. Now, for all of this to work, seeing that I just described a 2 neural network pipeline that needs training before it can actually deliver results, I developed a small so to say, training and test dataset with strings labeled for both tasks. And you can see an example of this here, where a string is labeled with the entities for the named entity recognition task, and a binary label for the interaction detection task. All of these work and the results of it can be seen here. And for the named entity recognition task, I use precision recall and F1 score as metrics, because these are the metrics that are most relevant to the task, and for neural network trained from scratch, I could say that they are pretty good results. And on the right-hand side, you can see the results from the interaction detection binary classification. All of this work put in extracting the relevant information from these documents goes into a platform that is intended to help medical professionals in detecting interactions between pediatric drugs. And the key advantage would be that the faster access to structured information. Now, the main types of interactions reported in the application would be between multiple drugs, or between a certain drug and an active substance, drug type, or disease. The application currently supports 3 main functionalities. That would be showing all interactions for one specific drugs, showing the interactions between drugs in a list, and showing the interactions of the last 3 types previously mentioned, so with active substances, drug types, or diseases. Some of the future, the ideas for future improvement include allowing the search for an active substance as an alternative to the search for commercial drug names, which was suggested to me by a professor from the University of Pharmacy, and also increasing the training data set so as to improve the accuracy. As well as extending the app to include all drugs available on the Romanian market, not just the pediatric drugs, which would mean that it could also be implemented in existing symptoms to provide this extra layer of safety that is to alert doctors if the drugs they're prescribing have interactions between them. And now I would like to show you a quick demo of the application. So it opens up with some details about the application, but that does not interest us. So the first functionality I mentioned would be that of showing all interactions for certain drugs, and we can type in a drug name here, and I'll pick a drug that I know has a lot of interactions. And here you can see for this specific drug, all of the drugs that it interacts with, as well as where the information was extracted from and the reason, as in the piece of text that mentions this interaction. And similarly, we can see the interactions with certain active substances, and this would be useful because if this drug interacts with an active substance, then it means that it interacts with all drugs that contain that active substance. And also the interactions with types of drugs, and why there are more of the same interactions displayed here is that is because there are multiple places in the documents where this interaction was mentioned. So, and similarly, you can see here the diseases which would generate adverse effects if you would administer this drug while having that disease. And quite similarly, we can see interactions between multiple drugs. And let's try 2 very common drugs. Okay, and here we can see what I called indirect interactions. That is, a drug interacts with, is set to interact with this active substance. So that means that it interacts with this other drug that contains that active substance. And similarly with types of drugs. And the last functionality would simply be that of checking interactions, for example, between a drug and an active substance, for example. And if you pick an active substance that doesn't have interactions, it would tell you so. But if it does, then again, you would get this result. So, that's it. Thank you for the attention. If you have any questions. Sure. From the LSTM. Okay. So in this part, I extract the drug references from the text, and for a specific. So I take the PDF for one specific drug. I know what that drug is, and for each small piece of text, I determine if it mentions an interaction or not. And then I flag the interactions, like for the drug for which I'm checking the PDF, and the entity is mentioned in the text. I don't know what that means. So. There are, for the English language, other approaches towards interaction, not exactly interaction detection, more like extracting medical terms from text and such. And a few machine learning approaches as well. But for the Romanian language, there's just one that is a bit similar, that deals with package inserts, like the documents that you would find when you buy a drug in the package. But that application is intended for the general population, so it would inform you about the properties of the drug, not the interaction still. So the LSTM network. No, just the architecture. I define myself. I use pre-built blocks for this part specifically.
No, I don't have other questions. Let's switch to the next presenter. So Bogdan Podaru, learning to cooperate using deep reinforcement learning. Bogdan Podaru, can you present?
Yes, hello everyone. Do you see me?
Yes.
I'm using my phone right now, but I want to switch it off on the presentation for not holding it because I don't have a webcam on my desktop PC. I'm presenting from my desktop PC.
I understand. Okay, switch the presentation, please.
Okay, thank you. Do you see the screen?
Yes.
Okay. I'm going to present you a way of how to learn to cooperate using deep reinforcement learning.
Good. Okay. Okay. So
human intelligence did not evolve in isolation. Both competition and cooperation led to a much more efficient way to solve problems because we are forced to adapt. The current trend is to develop software agents that integrate the results with human activity, or in other words, to cooperate with humans in order to achieve a common goal. One way to model such a setting is by using cooperative reinforcement learning. And if the agents act in a dynamic environment with a really large state space, we need powerful function approximation like deep neural networks. And there is a class of environments where the rewards that drive the agent's behavior are available only at the end of an episode. And these are the so-called sparse rewards and are really challenging to solve. And among multi-agent applications modeled with deep reinforcement learning, we find cellular network optimization for 5G base stations, online resource allocation in clusters, and traffic light control to reduce congestion. To study cooperation, I've introduced the problem called the escape room, which consists of two agents positioned in a room with a door and a button. The idea is that the door will remain open only if the button remains pressed and closing as soon as the button is released. So we can see that the only solution to this problem can be achieved only if one agent keeps the button pressed while other agent leaves the environment, both being rewarded a sparse +1 whenever one of them manages to escape. And the agents navigate with partial observations and map obstacles with LiDAR-like sensors to have the depth information about the obstacles around them. As original contributions, I've developed the escape room environment, which enables future work on fully cooperative environments. I've applied attention mechanism to avoid inattentional blindness. Inattentional blindness is a situation in which an agent can't sense an object or an event, even if it is in front of it. And we can think, and if we think of our problem, this translates in a situation where both agents simultaneously press the agent and none of them is moving towards the door. Another contribution is application of a technique called intrinsic motivations, and to incorporate this idea of intrinsically motivated agents. And I do this using options. And we can think of options in analogy to babies. In the beginning, baby is very interested in his body parts and starts playing with his hands and feet. We can think of his hands and feet as options. And as the baby grows older, the body parts become less and less interesting, and the baby focuses more on objects in its environment. And the last contribution would be the application of a recurrent architecture to capture these sparse rewards and to compose these options. And this has an important result, and this is an incorporation of memory into agents because they condition their decision to past activity. The related work is split between off and on policy methods. Off policy means that the policy uses both old and new transitions to update, while on policy uses only new transitions. And independent Q-learning is the most popular choice until now. In their paper, they study the cooperation in the Pong game, where agents have a negative rewarding scheme that pushes them to keep the ball in play for as long as possible. Independent Q-learning means running a different reinforcement learning and algorithm independently for each agent. But my work deals with partial observability and continuous action spaces, while they deal with discrete action spaces, and they require agents to have full access to the state space, to the state of the environment. Hindsight experience is a simple wrapper for existing off-policy methods. And it learns a hidden curriculum, a hidden set of skills that it uses to learn binary tasks, such as pushing and grabbing an object using a robotic arm. As I said, this hidden curriculum, this set of skills is hidden, is kept hidden. We can't control it. But the algorithm that comprises the techniques I already mentioned, called MAO, or multi-agent with attention over options, uses a set of reusable skills so we can control them. An example of a non-policy method is the emergence tool used from multi-agent autocurricula, or it is commonly known as hide and seek from OpenAI, where agents learn 6 adaptation strategies as a reaction of cooperation between agents. And this reaction is called autocurricula. And they compare intrinsic motivation with autocurricula in hide and seek environment. They use dense rewards, while this work, my work, uses intrinsic motivation to solve sparse rewards. Okay, the solution. The first technique, the algorithm MAO, is based on intrinsic motivation that guides the agent to explore the environment in absence of reward signal or in presence of sparse reward. And the idea is that an agent learns a set of reusable skills that it uses to control the environment. And for this, the traditional framework of interaction with the environment is split into 2 interaction environments, the internal and the external one. The internal environment, or the bottom portion of the image, as we see here, provides dense rewards and learns skills, while the external environment provides sparse rewards, and these sparse rewards are problem specific. A skill or an option is a temporally extended activity and is described by this tuple, where one option is available in a state only if that state is part of the initiation set I. If a decision is made to execute an option, the policy pi will infer actions or other options according to pi. For the escape room problem, we need 3 generic options, each being learned with a dense reward that allows normal conditions during optimization. And these options are moving to the button, moving to the door, and pressing the button. And as I said, these are learned using dense reward function. And for example, if we look at the last reward function and see that it is based on this function action press, which takes the value of 1 if the agent presses the button and takes the value of 0 if it doesn't. And if we evaluate this expression for not pressing the button, this will reduce to minus the reward scale. This means that the agent is penalized if it is near the button and does not press it. So this is how they learn these skills. The second technique MAO is based on attention over options. And assuming that the skills are learned, we already learned those generic 3 skills. How do we compose them? How do we find the order to achieve the problem-specific goal we aim for, that is to escape from this world? For this, we need to create a context in which the agent chooses an option. And for this, I use a policy architecture. We can see here in the top right corner, the policy architecture composed of an encoder, which extracts features from observations. And this observation could be leader sensor measures, the distance to the other agent, some mask to determine if the door and the button are visible, the door state, if it's closed or open, and so on. And this encoder takes this set of features, batches of features, and transform them into sequences of predefined length. And why I use sequences? Because I use an LSTM to create this context I mentioned, the context CT, by conditioning the option to infer on previous options. And the LSTM updates using sequences computed provided by the encoder. Another important part is the attention unit illustrated in the bottom right corner, which takes in regions, which are still observations, but with changing priorities. And these priorities can be learned during optimization. I choose as regions the distance to the button and the distance to the door for an agent to learn how to prioritize its action based on these regions. And the decision to weight more or less a region depends on the context, which is provided by the LSTM during interaction with the environment. Attention unit implements soft attention, meaning that it takes into consideration all the regions and doesn't left behind any of them or left out any of them. The decoder is a simple MLP with the output size same as the number of available options. This is an illustration of the MAO algorithm, which I'm not going to get into too much details. Multi-agent with attention over option, or MAO, is composed of two main parts. The first part of the experience collection part, steps 2 to 9, collects or interleave collecting option trajectories with action trajectories for the policies that sample options and for the policies that sample actions according to the execution of an option. And to favor this exploration, or this experience collection part to be more general, to favor exploration, the optimization takes place after K-start epochs. And to have relatively consistent decisions over time, policy optimization over option is delayed, has a lower frequency of update, such that the same option sampled in the same state leads to the exploration of the same state space. And then in step 10 and step 12, there is normal optimization of the critical and connector with a very popular deep reinforcement learning algorithm called proximal policy optimization. The tools I've used are OpenAI spinning up for optimization and monitoring statistics during optimization, multi-agent emergency environments for building up the escape rope setting, Mojoko simulator for visualizing agents' behavior after they were trained, and the results in the escape room. MAO achieves an expected reward of 0.5 out of 1, and the solution is received within 190 steps with a horizon of 250. MAO leaves the environment in about half of episode. This means the expected reward of 0.5. Compared to the traditional algorithms I mentioned already, independent Q-learning and fully observable critic from the paper hide and seek. And these algorithms are not able to capture sparse rewards at all. As you can see here from the bottom right image. And also from the top right image, we can see that MAO continues to improve. And these are the results after 2000 epochs. As a conclusion, I've developed the escape room environment whose solution can only be achieved through cooperation. I developed the MAO algorithm, which is based on two ideas, or it manages to learn both the skill set, the option set from scratch, and how to compose these skills to reach the final solution. And it uses attention mechanism to choose the most relevant regions in a cooperative context. While this sounds promising, possible improvements can be made, like lowering the learning rate or adjust the ratio between frequencies with which the policy over options and the options policy learn, and maybe more LSTM and attention units to capture longer sequences of observation. And I have a short demo to show you. Okay, so these are the agents which try to escape. One should press the button and the other should leave the environment. As we can see, one presses the button and the other do that, but let me stop here. Okay, here is a situation of inattentional blindness. Both agents stay at the button. None of them is going towards the door. Well, while this method reduces the chances for this to appear, it doesn't vanish it at all. And I have some references, and thank you for listening. And if you have any questions, please.
Which were the attributes which were inputted to your algorithm, and what was the size of the data set?
You mean the structure of my inputs?
Yes.
Okay, as I said here, the encoder takes in the observations from the environment, like leader-like sensor measures distance to the other or distance between agents, mask to determine if the door is or the button is visible. These are some simple flags, and the door state. The beauty of reinforcement learning is that it learns by self-playing. I don't have a data set. I just put the agents in the environment and they start interact with it. And they sample transitions and group them into episodes and use this to update. And because the environment starts with a new configuration each time, we can think of it that we can let them have some configurations for training, and after that choose those configurations that the agents didn't see till then and use for testing or for the test set.
Good, okay. Can you explain more? How did you measure the performance?
Yes, well, the idea is at the end of an episode, if the agent manages to escape the world, they receive a +1 reward.
Okay.
And during many episodes, I register how many times they manage to escape. How I sum up all these sparse rewards and some sort of divide it to the total number of episodes. And also a good performance is how fast they manage to escape. And this is measured in steps, where they start with a horizon of 215. This means that it can interact with the environment in maximum 250 steps. And if it managed to escape earlier from the escape room, that means the performance is increasing.
Okay, and
I can tell you that the solution could be reached in around 150 steps. So there is room for improvement.
It wasn't necessary to estimate the performance of the classifiers of the LSTM or something. Did you do so?
Well, the goal was the emergence of cooperative behavior, and this is the only way I can measure it by expected reward. This is what everyone does in the first place, measuring this expected reward.
Okay, thank you. Are there any other questions? Okay, let's continue. Edina Kando, visual acuity prediction based on features extracted from optical coherence tomography using convolutional autoencoders.
Hi, I'm Edina Kando. I'm studying computer science at Technical University, and my paper proposes a way of predicting visual acuity based on OCTs using convolutional autoencoders. As I've seen during this panel, this topic has already been presented by my colleagues, so I think that by now you are quite familiar with what OCTs are. But nonetheless, I'm going to do a quick overview of how OCT works. Let me just share my screen.
Okay, please.
Okay, can you see my screen?
Yes, yes.
Great. So to create a bit of context, I think that first of all, we need to understand how the human eye actually works. So if we take the eye anatomy, we know that this thin layer from the back is called the retina. And in very simplistic terms, it is responsible with capturing light waves that are sent through this lens and transforming those light waves into signals that are then furthermore sent through the optic nerve to the brain where the image is formed. In front of the retina, there is this small region called the macula, which is responsible with our central vision, while the retina is mostly responsible for our peripheral vision. This macula is also responsible with how we see colors, how we see fine details. So basically, thanks to this, we are able to read or drive and things like that. And in the center of the macula, there is this small pit called the fovea, where we have the highest visual acuity. So what is optical coherence tomography doing in this case is taking a cross-sectional image of the layers of the retina, an image that looks something like this. And what this helps with is assessing how assessing the thinning, the swelling, the thickening of these layers. As you can see here, there are some faint lines that separate the layers. I won't go into the medical terms because they are quite over my head as well. But what an optical coherence tomography generates is a series of slices known as B scans and another scan known as the fundus, which presents the macula and the fovea that I presented earlier. So if we were to take a simple analogy of what these represent, for example, if you imagine a cake, this fundus image would be the top of the cake, while the retina, the volume of slices would be what we would obtain if we were to cut the cake and turn it on its side and see the layers that compose the cake. So if you're wondering how this helps clinicians diagnose if there is a problem, with no medical background whatsoever, I guess just with the presentations that you've seen earlier, if we have a simple game of let's see which retina is the healthy one, I don't think that it would be a very difficult guess that the middle one is the normal retina, while the other two present AMD, or age-related macular degeneration, and wet AMD, which is the more aggressive form of AMD. I will be, of course, there are other diseases as well, but I will be focusing on these two. So what exactly is age-related macular degeneration? It appears when blood vessels grow and it results in some leaking fluid in the macula. If you can remember, the macula is the one responsible with our central vision. While not quite known what are the reasons for it appearing, there are some risk factors such as age. AMD usually appears in people over the age of 60. Of course, there are some genetics involved, smoking influences, the apparition of AMD, and also cardiovascular diseases, because these affect heart and blood vessels. And if you're curious how a patient with AMD experiences this disease, I have here a progression of wet AMD, and you can see that it starts with some visual distortions. So straight lines can be seen as bent. The central vision is obviously reduced. Difficulty in recognizing faces appears, and eventually a very well-defined blurry spot or blind spot appears. Since this affects the macula, so the central vision, and not the retina, which is responsible with our peripheral vision, in general, this does not lead to complete blindness. But nonetheless, it's quite a serious visual impairment. So how do we measure this visual impairment? The well-known Snellen charts. I think we are all familiar with this. They were introduced by Herbert Snellen in 1862. And how they work is that the acuity is measured relative to the ability of the normal population to distinguish a letter at 20 feet. So basically, if you have perfect vision, then you have 20/20 vision. But of course, there are some drawbacks in this Snellen charts, because they are quite a subjective form of measurement with a low repeatability rate. They are influenced by the clinician that takes the exam, and they are very dependent on the patient. So it's quite difficult to obtain the visual acuity for children, for example, or elderly with dementia or other health problems. So considering these difficulties, my paper tries to achieve three main goals, and that is speeding up the process of analyzing the three-dimensional volumes of B scans, which is quite an effort for an ophthalmologist. identifying a correlation between these scans and visual acuity, and predicting the visual acuity based on the OCT volumes. Of course, these objectives are not as easily achievable, so there are some main obstacles that I have managed to identify and unfortunately encounter during my endeavors. So the first of the obstacles is that the volume of B scans is actually a volume of images. So the computational power needed to process these images is quite high. The second problem is represented by the dataset. As you know, medical datasets are hard to come by. And the one I was using was a small dataset containing OCTs from 94 patients who were monitored in the emergency county hospital from Cluj. Some problems that I encountered with this dataset is that there were patients without visual acuity. The number of visits wasn't consistent, so I had patients with either 1 or 14 visits. The time interval between the visits is inconsistent, and also the optical coherence tomographies are captured with different methods. I won't go into detail on these methods, but the main idea is that they generate a variable number of B scans. So for example, if the fast method generates 25 B scans, the dense method generates 65. What is the proposed solution in this case? I tried to break down this into smaller parts. So for the first problem, the computational power needed to process the volume of B scans, I decided to use an autoencoder for dimensionality reduction. So how this would work is that I would encode each individual B scan, transforming it from a two-dimensional image to a one-dimensional array, while extracting some features from it, some key features. Afterward, I can create a volume of these encoded B scans, and as you can see, I would reduce the size of the input data from a three-dimensional volume to a two-dimensional matrix. The autoencoder that I've used for this was an adaptation of SegNet architecture. And I've chosen this because it has some known results in OCT segmentation, and it is efficient on small data sets. So the architecture of the autoencoder, as you can see, it is symmetric. And I am using a series of convolutions and max pooling layers for the encoder, and a series of transpose convolutions and max pooling for the decoder. The improvements that I brought to the classical SegNet architecture are replacing the upsampling layer with a transpose convolution. So instead of having a simple scaling up of the image based on nearest neighbors, like upsampling works, these transpose convolutional layers act as a convolution which upsamples the input while still learning the best method to do so. Another improvement was using binary cross entropy as the loss function, which I guess might sound a bit weird since most autoencoders use mean squared error, which of course was my first approach as well. But after some testing, I figured out that it didn't yield very good results. So since I've done some data pre-processing beforehand, and I've normalized all the pixels to have values between 0 and 1, I decided that I could use a binary cross entropy loss function for the autoencoder and consider that each pixel intensity can be interpreted as the possibility of that pixel being on, or the probability of that being on. In order to solve the problem of the small data set, which unfortunately results in overfitting, I decided to use transfer learning. As I've said, the dataset I used has a small number of OCTs, so I believed that if I were to train the autoencoder directly on them, I would be facing the risk of the encoder actually learning the OCTs from that dataset and not actually learning how to extract relevant features. So what I did was train the autoencoder on the Kermani dataset, which is currently the largest known dataset of labeled OCTs. And here is a high-level overview of how this transfer learning would actually work. So first, I would train this autoencoder on the Kermani dataset and extract only the encoder with the pre-trained weights and use it for my architecture and for encoding these B scans from the smaller dataset. For solving the problems of visual acuity and the different OCT capture methods that were in the dataset, I decided, I analyzed a bit the dataset and I decided to keep the data with the most frequent capture method used. So in this case was FAST in order to have the 25 B scan volume. Predicting the visual acuity was done using a simple convolutional neural network, a simple classifier. The steps were first, as you've seen in the architecture, I encoded each B scan using the pre-trained encoder. I created a two-dimensional matrix from the obtained latent codes, and I used a simple two-layer CNN for classification with 12 classes and as output that were corresponding to Snellen chart visual acuity measurements. As you can see here, the architecture, it's only 2 blocks of convolutions and max pooling, and with 2 fully connected layers at the end. And now for results and testing, in the case of the autoencoder, the Kermani dataset contained around 48,000 B scans, which I split into 80% training, 50% validation, and 5% test data. I used an Adam optimizer and I trained 5 different autoencoders with different latent code sizes. If you can see in this high-level picture, basically this latent code is a parameter for the autoencoder, and I played around with it a bit in order to see how far I can go until the autoencoder can no longer extract the most relevant features and can no longer reconstruct the image. As you can see, the loss did increase. I used an early stopping callback and it stopped the training at around 25 epochs. I used general batch size of 32 B scans. In order to measure the performance of the autoencoder, I computed the mean squared error between the original and reconstructed images. As you can see here, as expected, the latent code size of 256 had the smallest mean squared error, but for latent code sizes 128 and 64, we had very close values. But for code size, from code size 32 onward, we can see a doubling in this error, meaning that the features extracted are not that relevant, and this can be seen in the reconstructed images as well. Of course, that these images from the higher sized code are not exactly reproduced, but the autoencoders are not meant to be lossless forms of compression. This behavior is expected. In case of the visual acuity classifier, I trained the model on 600 B scan volumes. I used the autoencoder with the latent code size of 64. I consider that the small difference in error didn't compensate for the difference in size in order for me to use the one with size 256. I used the regular categorical cross-entropy loss function, and I achieved an accuracy of 90.62 after around 200 epochs with early stopping. As you can see, the loss function did decrease quite drastically, but the accuracy presents some issues. I believe that these are caused by the fact that the dataset is quite small. As you can see from the confusion matrix as well, there are a few misclassified OCTs, but they are from people with good vision, which I sort of lacked in this dataset. As you can see, for worse visual acuities, it works quite well because it was trained on those OCTs. As future work, I am in the progress, and I've started working on predicting future visual acuity. There is a very interesting article that uses time over convolutional LSTMs in order to solve the problem of inconsistent time interval between visits. Another method that can be used for visual acuity prediction could be random forest regressors. But in this case, what I would need to do is improve the autoencoder so that the feature extracted by it would have a smaller size, because random forest regressors don't work that well with such a large number of features. As a conclusion, I believe that I've proved that autoencoders can represent a powerful tool for feature extracting, and they can be used in several different domains and for solving several problems regarding OCTs. If you have any questions,
please tell us which is your original contribution reported to the state of the art?
My contribution is the update of the SegNet architecture in order to improve the autoencoder, and using the volume of B scans for visual acuity prediction.
Okay, thank you. Other questions? Of course.
Yes. Yes, I think it is okay now. Should I start from the beginning? Okay, okay. Okay. So, yes. My study revolves around presenting an approach to augmented reality content superimposition in a mobile environment achieved through analyzing the human body structure and using clothes overlapping method. So, because of the current pandemic, this situation emphasizes the importance of having accessible, easy to use online tools such that typical and physical presence can be avoided for certain activities. One of the obstacles of easily migrating into the online environment are the technical limitations regarding things like food tasting or trying on clothes. So my presented approach is an on-device real-time system of clothing overlapping. There are two main aspects, namely the estimation of the human pose and the actual overlapping of the clothes. In addition, there are facets to this core method, specifically the graph-based formalization of the problem and the segmentation of the clothing articles, which result in a better and modular way of overlapping the clothes. So even though the whole process of the proposed system is real-time, the pose estimation is image-based, which favors the use of a convolutional neural network. There are multiple ways and implementations for this problem, but for the pose estimation and detection itself, I use the Google ML-Kit pose detection API specifically for this task. In this way, the pose is detected and is estimated by the API, and one can focus more on the information provided by it and use it effectively for the problem of overlapping the clothing. So the clothes overlapping is done based on the information from the estimated pose. Every key point of the presented topology, which you can see here, from the pose detection API, holds positional information with which geometrical calculations are done to fit the clothing objects. Yes, there can be different ways of handling the fitting process, but the main idea which was implemented consists of segmenting clothing objects and overlapping them based on their respective body parts. So the clothing articles are meant to be one cohesive object captured in a single image, which is then segmented into different parts according to certain metrics. The process of splitting the clothing object into smaller segment images is actually done manually, and all the segments are then associated with the clothing article. In the current implementation, every clothing article has an associated graph structure to contain all segments and to create relations between the segments. So here you can see the graph structure. It is important to consider the graph structure associated with the clothing article, as this adds a lot of improvement possibilities for the clothing segmentation idea. This is modeled as a directed cyclic graph G, where V is the set of nodes and E is the set of edges in the graph. Each node V represents a clothing segment, with the exception of the root node, which is just meant to help traverse the graph G. And each edge represents the normally continuing segment according to human body parts. This means that the layout of the graph decides how to manually split the clothing object. The desired number of segments should be less than the maximal number of nodes in the graph G. My current graph layout is based on the segmentation from the clothing photo, and is basically a directed tree structure containing 9 nodes and 8 edges, not containing the root node and its outgoing edges. All in all, the graph G is meant to serve as a general layout for segmentation, but it also represents the form that the final clothing overlapping should take. What this means is that even while the graph remains unchanged for clothing objects, the resulting overlap of fitted clothes will actually respect the same ordering of segments as presented here in this graph. If a certain clothing segment is meant to represent the upper left arm as a node in G, it will still be placed as the upper left arm clothing in the resulting content projection. This property ensures that choosing a correct layout of the nodes and edges in the graph for the respective clothing object is affecting the preview of the clothing overlapping. For the fitting the clothing segments onto the human body shape, the algorithm was actually divided into 3 parts, going through the graph structure and ordering the clothing segments. For specific pairs of body joints from the pose estimate, preparing container polygons for the segments and fitting the segments into the polygons for the respective frame. So the first step, the segments are taken from the previously defined graph of clothing parts Every segment will correspond to a certain body part, which is determined from the detected pose of the respective frame. As an example, the torso segment will correspond to a polygon defined by 4 body joints, namely the left and right shoulder and hips, while the other segments will actually correspond to a personalized polygon construction based on the 2 body joints. And you can see the construction here in this photo. In step 2, the container polygon for the clothing segments are prepared. In this case of the torso, the polygon is already defined by the 4 body joints, which are already obtained by the pose detector, so there is no need for additional calculations. We now can see the case for limbs defined by only 2 joints, for example, arms and legs. In this case, a special construction is implied, which is this photo. And finally, in the last step, this step consists of the actual fitting of the clothing segments to the newly created polygons. The clothing segment is taken as an image, adjusted based on the transformation metrics. The undertaken operations being translation, rotation, and scaling of the clothing segment based on the container polygon information and the previously computed angle. So, after all required body parts have been overlapped with fitted clothing segments, there are several adjustments made in order to also provide an overall fit of the clothing. Here the idea is to avoid certain loose fits which are mostly caused by imprecise pose estimation, referring more to imprecise placement of the body joints. After the individual fit of the clothing segments, there are situations where polygons look disconnected, like here in this photo, and provide an inaccurate depiction of the clothing overlap. The idea used here consists of 2 correcting aspects, first being offset for transformation metrics translation and slightly resizing container polygons based on their corresponding neighbors of the graph. Because the pose detection is done in real environment, it is subject to abstractions or certain other factors like how close the camera to the human body is, which can lead to joints being approximated slightly shifted from where they actually should be. This can make a visible difference for clothing overlapping, and thus offsets are also approximated based on how precise the estimate should be. In principle, the smaller segments like the ones from arms have bigger offsets as they tend to look more displaced in case of a loose estimate. And now I will show you how it actually looks. So as you can see here, in principle, the person can move completely freely in space because the pose estimation and detection also offers depth perception. In practice, some of the movements offer irrelevant projection. For example, a 90-degree turn showing the person's side's body would show no overlapped clothes. This happens because the clothing segments and the overlapping process are 2D images based, but not all rotations are taken into consideration, which means that in the previously mentioned case, the clothing segments will be considered as lines parallel to the y-axis, thus will not be shown on the screen. The width of the image would be 0. In this case of a degree bigger than 90 degrees turn of a person, the clothing is rotated and then the overlapping process adjusted for this context. As a result, the user is allowed to partially move freely in the sense that some movements and rotations offer no actual visible and relevant information. So, in conclusion, the mobile application provides real-time performance feedback through the means of metrics like frames per second, frame latency, and pose detector latency. And I tested this proposed system on 2 different Android devices, Samsung Note 20 and Samsung A10. And the obtained measurements are the following, the last version of the implementation. So thank you for your attention. If you have any questions.
Thank you, Teodora. A very big question. Other approach, the literature.
So many of the approaches from the literature are actually mixed reality or virtual reality, where they actually build a 3D model. So it's not actually on the body, in real time. They actually build the 3D model based on the human body. But a similar one which uses augmented reality exists, but it does not use a graph structure like mine. And I chose this graph structure because it can easily be extended. For example, the lower arm can be extended to much smaller pieces, and the representation can look more accurate in the final product.
Thank you.
Thank you.
I don't have further questions. I assume the panel is over. Okay, so thank everyone for the interesting presentations. Okay, I think we have to switch on the Commission channels. Of course. Thank you.